supremely powerful mathematical tool which has been used over the centuries to drive new physics. Calculus is really a part of mathematics, but physics and mathematics are inseparable. Maths is the language of physics, and you can imagine it like the bedrock that the world of physics is built from. Newton also made strides in the field of optics, which is the physics of light and how it travels through different materials. It explains refraction seen in prisms, and lenses which are used to focus light in telescopes, microscopes and cameras. Telescopes enabled us to peer into the depths of space and observe the wild array of objects there, and developed astrophysics and cosmology. Optics is closely related to the theory of waves, which is basically how energy can travel through disturbances of a medium, like ripples on the surface of a pond or sound through the air. Light doesn't need a medium to travel through. It can travel through the vacuum of space, but it still follows the same principles as all waves, namely reflection, refraction, and diffraction. This leads us to electromagnetism, the description of magnets, electricity, or more generally, electric and magnetic fields. It was a physicist called James Clerk Maxwell who discovered that these are two aspects of the same thing, and derived the wonderful element called electromagnetism, and theorised that light was an electromagnetic wave. Electromagnetism also explains all of electricity. Jumping back a little bit, classical mechanics is related to Newton's laws and covers the properties and motion of solid objects, how they move when forces hit them, and what happens when they're joined together like in gears or pillars. Fluid mechanics is the description of flows of liquids and gases. Using fluid mechanics you can work out how much lift is generated from an aeroplane's wing or how aerodynamic a car is. Fluid mechanics is notoriously difficult, mostly because the motions of tiny things like molecules get really complicated really fast, which leads us to chaos theory. Chaos theory is the description of large complex systems, how small differences in initial positions can lead to very different final outcomes. Thermodynamics is the description of energy and how it passes from one form to another. It also includes entropy, which is a measure of order in the world, basically tells you how useful different kinds of energy are. Energy is a fundamental property to physics, and although I've written energy here, I should have written it everywhere in math, because everything is energy. So that's all of classical physics, a picture of the universe we had around the year 1900. It told us we lived in a universe where everything ran sort of like clockwork. If you could measure everything accurately enough, the future was kind of predetermined. However, not everything was solved. There were just a few holes in experiments that hinted at something more. The orbit of Mercury was slightly too fast, and some strange things happened on the smallest scales with electrons and light, which were all unexplained. Physicists at the time thought that they'd solve and explain these problems soon enough, but poking at them, they unravelled the new domains of relativity and quantum physics and turned our understanding of the universe completely on its head. Albert Einstein was the genius who developed the theories of special and general relativity. Special relativity predicts that the speed of light is constant for all observers, which means that when you travel really fast, weird stuff starts happening, like time slowing down. It also states that energy and matter are different aspects of the same thing through the famous formula E=mc². General relativity says that space and time are part of the same fabric called space-time, and that the force of gravity comes from objects bending space-time, making other objects fall in towards them. While relativity describes the very big, other physicists were busy at work on the very small world of quantum physics. Atomic theory probed the nature of the atom, and more detailed descriptions of the atom were developed. From a tiny sphere to electron orbits, to energy levels, and then to the electrons being wave-like charge distributions. Condensed matter physics describes the quantum physics of many atoms together in solids and liquids, and is where many great technologies have come from: computers, lasers, and quantum information systems. Nuclear physics describes how the nucleus of atoms behave, and explains radiation, nuclear fission, the splitting of an atom used in our nuclear power, and nuclear fusion, which takes place in the sun, hopefully soon be harnessed here on Earth. Particle physics probes even deeper to find the fundamental subatomic particles that everything is made of, and are described in the standard model of quantum physics. And quantum field theory captures all of quantum physics, combined with special theory of relativity, and it's the best description of the universe we have. Unfortunately, quantum field theory doesn't include gravity, so physicists don't know how to join together quantum physics and the general theory of relativity, leading to a giant chasm of ignorance. One day in the future we hope to close this chasm and come up with a theory of all of physics, called quantum gravity. And there are many examples, string theory, loop quantum gravity, and many more. But quantum gravity isn't the only thing we observe but don't understand. There are also major puzzles of dark energy and dark matter, which seem to make up 95% of the universe. So all of our physics only really describe 5% of what is known, and everything else, most. And there are many other mysteries out there, like the Big Bang, and no doubt there's things beyond that we don't even know that we don't know. Which gets to the lofty cloud which floats over all of physics, philosophy. Although many physicists make fun of philosophy, it's the big philosophical questions that motivate a lot of physics, like what is the fundamental nature of reality? How come the universe even exists? Do we have free will if we're just made of physics? Or how do we know that the way that we do physics and science actually gets to the fundamental truth of the universe? And just why is all of physics like the way it is? Well, those are rather big questions, ones which we may or may never answer, but there's no reason to give up trying. After all, physicists are not quitters. And that was the map of physics. So that's the end. Thanks for watching the video. I hope you enjoyed it. I'm still kind of working on the format of this channel. The universe is made of matter.
Over the last 52 weeks, I've enjoyed sharing with you my fascination with biology. If you've been through it with us, you've now got yourself a pretty deep and complex understanding of how life functions, from the chemistry that makes cells work to the ecosystems that make the planet work. And it's never too late to catch up on those biology and ecology courses. They'll be here on YouTube forever, but it's time to move on to something new. Something bigger because it's smaller, more beautiful because it's invisible, more powerful because it's everything. Crash Course Chemistry. My undergraduate degree is actually in chemistry, and I've been a lifelong lover of this subject, not just the rules and the laws and the bonds and the coefficients, but of the men and women who shaped this science that deepened our understanding of the world so magnificently. The Siberian misanthrope who would revolutionize our understanding of matter, the German war criminal who saved 1 billion lives, the French aristocrat who created the science of chemistry, and all he got for his trouble was beheaded. And of course, all of these stories exist within the greatest science ever. What is matter made of? How and when do atoms come together and break apart? What is an electron? Why is silver's chemical symbol Ag? How do we fix global warming and live forever? The answers to all of these questions, except for the last two, will be contained within this course. But those last two, if and when they get solved, I guarantee you, will be solved with the help of chemistry. And we'll be doing it in this beautiful new set that was designed and created by Nick Jenkins and our graphics team. Our graphics team will be Thought Cafe, which is what Thought Bubble has turned into. We're slaving away on Crash Course Chemistry now, and the first episode should be hitting your subscription box within the next couple of weeks. Until then, feel free to check out any of the biology that you may have missed, and we'll see you soon.
Recalculating route.
Hello, I'm Hank Green, and I want to teach you chemistry. Please, do not run away screaming. If you give me 5 minutes to try to convince you that chemistry is not torture, but instead the amazing and beautiful science of stuff, and if you give it a chance, it will not only blow your mind, but also give you a deeper understanding of your world. This is just my opinion here, but I think that understanding the world leads to a greater ability to enjoy the world, and there's nothing that helps you understand the world better than chemistry. Chemistry holds the secrets to how life first formed, how cancers are cured, how iPhones have bigger hard drives than 5-year-old laptops, and how life on this planet might just be able to continue thriving, even ours, if we play our cards right. Chemistry is the science of how three tiny particles, the proton, the neutron, and the electron, came together in trillions of combinations to form, get this, everything. Now, chemistry is a peculiar science, sometimes talked about as a bridge between the ultra-abstract world of particle physics and the more visible sciences like biology. But calling chemistry a bridge is like calling Eurasia an island. Chemistry has it all. Mad scientists, world-changing revelations, the practical, the impractical, medicine, bombs, food, beauty, destruction, life, and death. Answers to questions you never knew you had. I love chemistry, and I hope I can give you a glimpse into why. So today, let's start out with maybe the biggest idea of all time and move on from there. Stuff is made from atoms. I know. You aren't shocked, you aren't awed, you might not even be paying attention anymore, but when atomic theory was first proposed, it sounded pretty crazy. And yes, we call it atomic theory, using the scientific definition of theory, which is a well-tested set of ideas that explains many disparate observations, not the colloquial definition of theory, which is a guess. Though luckily there's no one running around anymore saying, atoms are just a theory. But it wasn't that long ago that people were running around saying that, and you wanna know who settled it for good? Einstein. Atoms had been postulated for a long time by the 20th century, but it wasn't until Einstein mathematically proved the existence of atoms and molecules in 1905 that the matter was truly settled. And you thought Einstein was all about relativity and E equals mc squared. He also proved atoms exist. Here's how it happened. In 1827, a botanist named Robert Brown was looking at pollen grains in water through a microscope, and he noticed that they jiggled randomly even when there was no movement to cause the jiggling. It was a mystery for a long time, until 1905, when Einstein theorized that this phenomenon was caused by as yet unproven atomic particles actually smacking into the grains of pollen. He wrote up some fancy math, showing that his theory predicted this motion almost perfectly, and everyone had to concede that yes, tiny discrete bits of matter were indeed smacking into the pollen, and thus molecules, and by extension atoms, must exist. Today, we remember this botanist and his discovery by calling the motion he observed Brownian motion. It's kind of crazy that every physical thing you've ever interacted with is made up of little ball thingies. It started with people wondering what would happen if you just kept slicing something in half forever. Eventually, and of course it turns out that there's no knife sharp enough to do this, you end up with one pure unbreakable bit of that substance. The word atom, indeed, is from the Greek for indivisible, though, of course, as we learned in World War II, atoms can be broken as well. So all the stuff that we think of as stuff is made of atoms, tiny, discrete particles that have specific properties depending on the arrangement of three simple subatomic particles. There's the proton, heavy and positively charged, the neutron, about the same size as the proton but neutral, and the electron, which has the same amount of charge as the proton, just opposite, and very nearly has no mass at all, about 1,800 times less massive than the proton or neutron. Protons and neutrons hang out in the nucleus, and thus are the nuclear components, or nucleons. Electrons hang out around the nucleus and are the parts of the atom that do all the interesting chemical stuff. But before we get to the chemistry of the electrons, we first have got to understand the properties of the nucleus. Okay, this is pretty important, so pay attention here. The number of protons in an atom determines what element it is. 79 protons, always gold. 59 protons, always praseodymium. The number of protons in an element is its atomic number. It sits right on top of the box in the periodic table because that is the element's defining trait. So an atom of silver with 47 protons in its nucleus is always an atom of silver. Depending on what its electrons are doing and what it's bonded to, it might be part of a chemical that's silver-colored or black or blue or shiny or poisonous or a cure for disease. But whatever it is, that atom is still silver, and will remain an atom of silver probably forever, because that core number is very, very difficult to change. Now you might have noticed something weird about silver here. Its chemical symbol, the 1 or 2 letter short code that tells you what it is Ag, not Si, which is silicon, or Sv, which is perfectly available, but Ag. Why? To torture you? No. Silver, of course, because we've known about it for a long time, was one of the first elements added to the periodic table, and back then it was called argentum, Latin for shiny gray stuff. Also, the root of the word Argentina, where Spanish explorers heard rumors of mountains made of silver, which of course did not exist. The name Argentina, just like the chemical symbol Ag, stuck, despite neither of them being particularly representative of reality. Now, back to science. Nuclei, which is the plural of nucleus, are boring. They're thousands of times smaller than the atom as a whole, and they mostly just sit around being exactly the same as they were when they were first created billions of years ago, held together by the strongest of the four fundamental forces of physics, the strong nuclear force. The fact that nuclei are so boring is the very reason they're the defining characteristic of elements. While electrons can jump from atom to atom whenever it's convenient, the number of protons is almost always extremely stable. So that core of the atom, the nucleus, always comes out of chemical reactions unscathed. It's the bit that we can bump around from reaction to reaction, but always remains pure and behaves the same way as any other atom with that number of protons. The atomic number is the soul of the atom. It's what makes it it. Neutrons are important too, of course, in their own way, but they don't change what element an atom is. One of the two keys to all things chemical is charge. We'll discuss that in another episode, and since neutrons don't have any charge, they mostly don't change the properties of an atom. But they are nonetheless vital. We all know that like charges repel each other. Neutrons serve as a kind of buffer between the protons. You couldn't pack silver's 47 protons together in the nucleus by themselves. They couldn't handle it. They'd rip themselves apart. So nuclei only clump together permanently when the right number of protons and neutrons get together. Silver needs about 60 neutrons to space out the 47 protons correctly. But it doesn't have to be 60. In fact, silver nuclei are also very stable with 62 neutrons. 61, though, that doesn't work. And the reasons for that, I don't know. You would have to talk to a nuclear physicist. The atomic number of silver doesn't change as the number of neutrons because the number of protons is the same. But the relative atomic mass does change. Relative atomic mass, which used to be called atomic weight back when I was in school, is basically the number of protons plus the number of neutrons averaged across all the silver on Earth. Because silver has two different stable isotopes, each with a different number of neutrons, its relative atomic mass ends up not being a whole number. About 52% of silver has 60 neutrons and about 48% has 62. The relative atomic mass then ends up being about halfway between 107 and 109, 107.8682. You'll note that I said these two different sorts of silver are called isotopes. They have different masses but the same chemical properties and are the same element and so belong in the same place on the periodic table. In fact, the word isotope means same place. And different isotopes have different mass numbers. The mass number is just the total number of nucleons in the nucleus, which is different from atomic mass. It's simple addition for a single atom rather than an average of all the relative atomic masses of all the silver atoms on Earth. So silver has two stable isotopes, one with a mass number of 107, which we'd call silver 107, and one with a mass number of 109, silver 109. There's an easy way to write all this out, of course, to keep your information straight. The chemical symbol with the atomic number or number of protons here, the mass number or number of protons and neutrons here, and the charge out here, which tells you by simple addition or subtraction how many electrons there are. Finally, before we conclude this first episode of Crash Course Chemistry and thus our discussion of the atomic nucleus, a note on the pronunciation of nucleus. You are welcome to say nucleus. It is an accepted pronunciation of that word, but if you can find it in you, it's probably best to switch over to nucleus, which is, after all, how it's spelled. And that is all for today's episode of Crash Course Chemistry. If you were paying attention, you now know more about atoms than anyone did in 1900, like that they were finally confirmed when Einstein mathematically defined Brownian motion, that elements are chemically pure substances, and the type of element an atom is defined by how many protons it has in its nucleus, or its atomic number. That neutrons stabilize nuclei for their proton friends, that different isotopes of the same element are the reason relative atomic masses are never whole numbers, and you know that nuclei are the uninteresting, boring bits of the atom, and the electrons are where all the interesting chemically stuff happens. Crash Course Chemistry is filmed, edited, and directed by Nick Jenkins. Dr. Heiko Langner is our chemistry consultant. Sound design is done by Michael Aranda, and our graphics team is Thought Bubble. If you have any questions, comments, or ideas on any of this stuff, we will endeavor to answer them in the comments below. Thank you for watching Crash Course Chemistry.
2,640 liters.
1 foot, 2.3 kilograms, 9 volts. I just closed the circuit with my tongue and I felt all 9 volts. So what do all these things have in common? They're units. Yes, but they're also absolutely, completely arbitrary. You know who decides how much a kilogram weighs? A hunk of platinum and iridium known as the International Prototype Kilogram, or IPK. The IPK isn't just how much a kilogram weighs. In a very real sense, the IPK is the kilogram. Every other kilogram is exactly the same as the IPK, and the IPK is the lump of metal that decides what that mass is. A kilogram is defined as being the same mass as the IPK. We made kilograms up, just like we made up seconds, weeks, and volts and meters. There's nothing about these things that makes them them. Someone just decided one day that that was a kilogram. Now, the fact that I find units fascinating probably says more about me than it does about units, but I could talk about them all day. For example, did you know that the International System of Units only includes 7 base units, and every other unit is derived from those units? Speed is length divided by time. Acceleration is speed divided by time again, so meters per second per second. Force is that acceleration multiplied by mass, because F equals ma, remember? Work done in joules is force multiplied by distance. And power is work divided by time, so how much work can be done per unit of time. Makes sense. It goes pretty deep, and it's absolutely correct to say that there are an infinite number of possible derived units, just most of them aren't useful enough to name. But here's a bit of trivia for you. When I say watts or hertz, those things are just regular words, no special capitalization necessary. But hertz and watt, they were real people with, like, last names that were capitalized. So what's up with that? Well, getting a unit named after you is kind of the holy grail of science. To quote Richard Hamming, true greatness is when your name, like hertz and watt, is spelled with a lowercase letter. Of course, when these geniuses were first piecing together how the world worked, they had no idea that there were fundamental basic units beneath it all. They were basing all of their units on arbitrary values because, well, how could there possibly be a fundamental amount of mass or distance? Interestingly, one of the standard base units is derived from an actual value, though not a universal one. The second is 1/60th of 1/60th of 1/24th of the time it takes for the Earth to rotate a single time. That's something, at least, but it also illustrates an interesting point. As fundamental as that seems, when you get down to the dirty details, things start to get kind of cloudy. The Earth's rotation, for example, is slowing down. Does that mean that seconds should also slow down? No. That would mess up every calculation ever. So seconds are slowly becoming less and less based on reality. Now don't worry, it's going to take forever for the Earth to slow down noticeably, and when it does, we'll just keep adding leap seconds to keep things balanced. But units are extremely important in chemistry and in sciences in general, as we learned when the Mars Climate Orbiter crashed into Mars because instructions were inputted in the wrong units. Next time you get a B instead of an A because you didn't keep track of your units, just remember, at least you didn't destroy a $300 million mission to Mars. But what do I mean when I say keep track of your units? Well, I mean watch them. Do not let them do anything you didn't tell them to do because they're sneaky. And a lot of chemistry is just converting between units. So say you're in a car, and the car is going 60 miles per hour. Now, right now, everyone who doesn't live in America is like, boo, miles are terrible. Convert to kilometers, Hank. Well, I'll do you one better. From a scientific perspective, kilometers are terrible too. They're just as arbitrary. We should use something more universal, like light years, the amount of distance light can travel in a year. And hours is no fun, so let's convert to light years per second. 60 miles per hour. When you say it, it sounds like a whole number with a single unit, but it's not. It's actually a fraction. 60 miles over 1 hour. Let's start with the easy part, getting to seconds. So first, we've got to get to minutes. So there's 60 minutes per hour, and also 1 hour per 60 minutes. That fraction, once we have it, can flip either way. We want it with the hours on the top, on the numerator. Why? Because we want the units to cancel. We want to destroy the hours. We don't want them in our units when we're done. Then the same thing happens again with 1 minute per 60 seconds. Now we go to light years. I asked Google, and there's 1 light year in every 5.9 times 10 to the 12th miles. Looking at this, we see that the hours cancel, and the minutes cancel, and the miles cancel, leaving us with light years per second. That's really what matters. We've come out with the correct units. The rest is just hammering at the calculator to discover that a car going 60 miles per hour is also going 9.3 times 10 to the negative 12th light years per second. Now we perform an important test, the does this make sense test. And yes, indeed it does, because 9.3 times 10 to the negative 12th is a very, 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 very small number, which makes sense because when you're traveling in a car, you're going a very, 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 very tiny fraction of a light year every second. Now there are probably gonna be 50 to 100,000 people that watch this video, and I'm gonna guess that maybe a solid 7 of you did the math along with me with your calculator out. Now, I'm not giving you a hard time, that's just my guess. If you want to follow along with your calculator in the future, that might be helpful. It would at very least be very nerdy. But if you had been following along with your calculator, you might maybe have noticed something interesting. I said 9.3 times 10 to the negative 12 was the calculator. The calculator probably said something like 9.3487658140029 times 10 to the negative 12th. So why, when I had so many more numbers to give, did I only give 2? Was I trying to save time? Well, obviously not, because now I appear to be wasting time talking about it. Do you think that it would be too hard for me to remember all those numbers? Well, obviously not, because I just did it. So I will tell you why. When you're doing experimental calculations, there's 2 kinds of numbers. There's exact and measured. Exact numbers are like the number of seconds in a minute, or the number of eggs in a dozen. They're defined that way, and thus we know them, in effect, all the way out to an infinite number of decimal places. If I say that there are a dozen eggs, you know that that's 12. Not 12. It's 12. So that's not true for the number of miles per hour my car was going. That car wasn't going 60.0000 out into infinity miles per hour. I only know the speed of my car to 2 decimal places because that's all I get from the speedometer. So the car could have been going 59.87390039 miles per hour or 60.493212 miles per hour. The speedometer would still say no matter how well I measure the car's speed, I will never know the same other decision that I will. So that's the second type of measure. Not a good thing about measured numbers because you never ever know them exactly, because they tell you 2 things at once. First, they tell you the number that you measure. And second, they tell you the precision. People often get their heads around this, but with a measured number, you just have to remember that the actual number goes out to infinite decimal places. You just never know that. You can't. It's impossible. So when my scale said 175 pounds, that doesn't mean 175.0000 pounds. 175 point something. With all those numbers out to the 5, we don't know it. Here's the thing. A measured number can be pretty unhelpful if you don't have knowledge of the precision of the measurement. So you have to conserve the precision of your calculations, or else you might end up So we have a set of rules for what are called significant digits. These are the digits in the number that you actually count. With my speedometer, there are 2, 6, and 0. But 0 is weird, because sometimes it's just a placeholder. Like if I said that the fastest plane can go 50,000 miles per hour, which it can, by the way. An unmanned military test glider did it in 2011. That's not an exact number. Those zeros are just placeholders. So when a number ends in a 0, or 2 or 3 zeros, it's hard to tell if those zeros are significant. But this all gets so much simpler when you use scientific notation, which since it's science, we should. So 60 miles per hour would instead be 6.0. How? We get the 0 is significant because it's close, otherwise it would be 60 miles per hour. Keep that 0 around because we actually know. Scientific notation is awesome, by the way, once you get the hang of it. If you're having trouble, you can always just type it into Google.
Well, thank you very much. It's wonderful to be here again. Now, yes, this is the International Year of the Periodic Table. Currently, there are 118 elements, different elements, and the periodic table is trying to bring some sense, some order to this vast number of elements that we have. The song, of course, was in pretty random order, so there was no sense behind that, and this is what the periodic table is all about. And as you've heard, as I'm sure you all knew before, this year, 2019, is the International Year of the Periodic Table. And that's because it is the 150th anniversary of the publication not actually of the very first periodic table, but the first one by this chap, the Russian scientist Dmitry Mendeleev. So he first published his version in 1869, and this is shown here. It's in Russian, so it's rather difficult to read. It says Chimie, the top there, but this is his table. It's slightly different from our modern version. In this one, well, in our modern version, we see that groups of similar elements with similar properties are arranged in vertical columns, which you see at the moment. In this one, they go up slightly changes. With this one. The printed one that I just showed you actually is one that's in the collection of St Catherine's College in Cambridge, and this is a display we put on the drafts of the exhibition. The exhibition is going to be built in London. It's going to the University of Chemistry in August. So you can go and see not only Mendeleev's version, but very, very from 7 years earlier, which is really rather interesting because it wraps around the cylinders. This one here, you might realise that this isn't some sort of photoshopped version. This is actually set up on the grass. And they're all different sizes and all placed in exactly the right position, so that when you stand just backwards, order comes to the elements there, and it looks like that. So this was really a photograph that was taken. This is inside the exhibition. As I say, do go and see these things when they come to the Royal Society of Chemistry to Burlington House. There's all sorts of different forms of display. In fact, the long shaft of the tool cabinet is the very, very, very first periodic table, which is really exciting. Very different. But hopefully after today, you'll understand what makes it. They can look quite different indeed. This is what was donated to the college, commissioned for us for this year, the International Year of the Periodic Table. It's absolutely amazing. It's made out of silver, and it really is a periodic table. It looks very different from the versions that we're going to be looking at today and we're familiar with, but nonetheless, it still works. So go and check this out if you get a chance in August. Well, we're going to be sticking with our more familiar form, but we need to understand exactly what it is that makes a periodic table and how it works. And in order to do this, we need to understand the very structure of the atom itself. Now, as far as a chemist is concerned, atoms are we have positively charged protons in the heart of the atom, the nucleus, and sometimes, well, almost always, apart from one atom, we have neutrons, which have no charge at all. And then whizzing around the outside, we have negatively charged electrons. And so long as it's a neutral atom, we have the same number of positively charged protons and negatively charged electrons. Physicists, of course, love smashing things up even further and breaking everything, but we're not going to be concerned of what we could smash those things up into quarks and things, all sorts of nonsense like this. We're just going to stick with our lovely protons, neutrons, and electrons. So let's go to the very, very first atom, and this is hydrogen. So where is hydrogen? Right at the top there, very good. So you are atom number 1. The first atom in the periodic table, the first element. And what makes you unique and different from every other one is that in the heart of the nucleus, you have just one proton. Okay, that's what makes a hydrogen atom. And in the neutral atom, it's balanced by the electron, one electron whizzing around there. So this is what we see. When we go to the next atom, well, this is the element helium. So right the way over here, very good, helium. Okay, so there's helium. Well, helium now has 2 protons in the nucleus. It happens to have most of the helium that we come across also happens to have 2 neutrons. We're not going to be interested in neutrons. They increase the mass of the atom and of the nucleus there, but they don't really alter its chemical properties. But what makes helium special is the fact that unlike hydrogen with only 1 proton, helium has 2 protons in the heart of the atom, balanced by, in the neutral atom, 2 electrons whizzing around. And then we come to atom number 3, we're back over here again, which is lithium. Oh, already there, look at that. Okay, very quick. So element number 3 here, lithium, 3 protons in the nucleus there. Okay, now we're going to move across. So element number 4 is beryllium. Okay, so 4 protons, 4 electrons. Then we come back over to this side with boron, 5 protons, 5 electrons, carbon, 6. Okay, then we have very good carbon, nitrogen, 7. Okay, oxygen, 8. So each time we're increasing by 1 proton, nitrogen, fluorine here with 9, and then neon, 10, And then we come all the way back to this side, and we come to the element sodium. 11. Good. Okay, well, so far so good. Now, I'm not going to go through all 118. That would be just a little bit tedious. But this is the underlying order. It is the order of their atomic number. This is the number of protons in the heart of the atom. But there's more to a periodic table than just having them arranged in order. We also need to group the elements of similar chemical properties in these vertical groups. This is really important, and this is what any periodic table must achieve. So we've got this underlying order as we move from one element to the next, where always each atom is getting heavier, and we're adding more protons and electrons. Okay, but we also need this order with similar properties. And this is what we're going to look at now. So let's have a look at group 1. So these are all the purple ones. So if you've got a purple card, hold it the card. Okay, well done, very good. So these are the group 1 elements. Now what they all have in common in terms of their atomic structure, we'll see some of their chemical properties in a moment, but what they all have in common is that they all have just one electron in their outermost shell. Of course, hydrogen only has one electron anyway, but then all of the others have one in their outermost shell. So let's look at lithium again. Lithium has, well, 3 electrons in total, 3 protons, but there's one in the outermost shell. We come to sodium, 4 electrons, but there's still one in the outermost shell. And it's relatively easy to lose that one electron, and this gives it similar properties to lithium, and in some ways even to hydrogen. We keep on going, potassium, so the nucleus in the heart of the atom there is getting bigger and heavier, the atom is getting heavier, okay, but there's still one electron right on the outside there whizzing around, which gives them all similar properties. Let's go to rubidium, getting pretty massive now, loads of electrons. There's still that outermost one. We get to cesium, really craziness going on now. But there's still that one electron whizzing around. It's quite away from the nucleus. It means it's quite easy to remove that one electron. That is what gives this its chemical properties. We'll look at these in a moment. Okay, but they all have something similar. There is, of course, francium, the heaviest element in this group. I'm not going to show francium because there'll be too many electrons, but also because actually francium, I'm afraid, falls apart quite easily. This is where, well, for the very heaviest of elements, the nuclei are getting so large that basically bits fall off, essentially. This is actually radioactive decay. What happens is, for instance, we could lose 2 protons, 2 neutrons. This is the heart of a helium atom, essentially. So an alpha particle is a helium nucleus. This can ping out, and then it's changed into a different element. So this is why we're not going to be looking at the very, very heaviest elements in the group set, because these are unstable and radioactive. So cesium is one that we can look at. It is stable, but it has this one all-important electron whizzing around there. So that's our group 1. So here they all are again. So let's just see group 1 again. So all the purple ones all have one electron in the outermost shell. Then we move to group 2. So group 2, the orange ones, very good. You're very busy, aren't you? You've got 2 to do, yes. Okay, so group 2 here all have 2 electrons in the outermost shell. And this gives them similar properties to each other, as we shall see, but different from those from group 1. Okay, we're going to move around all the way to here now to the brown cards. So these are group 13. Okay, or sometimes called group 3, and there are good reasons for this. They all have 3 electrons in their outermost shell that they can use. Okay, we come to group 14, the dark grey ones, 4 electrons, very good. Group 15, the light blue, very good. All beautifully aligned, all with 5 electrons in the outermost shell. 16, the nice yellow ones, very good. 6 electrons in their outermost shell. Sulfur's a little bit the wrong way up, but it doesn't matter because it works either way. And then we have group 17. I like these ones. These are these so-called halogens. We'll come back to those in a moment. And then right on the end, the final ones here, we have group 18, the so-called noble gases. Okay, we'll come to those in a moment as well. Let's go back for a moment to the halogens, so the green ones. So just show us again our halogens here. Okay, these are one of my favorite groups. These are some of the most reactive elements in the whole periodic table. So fluorine, in fact, when this was first put into the periodic table, into Mendeleev's periodic table, the element hadn't even been prepared yet. They knew it was there. It was in certain salts, so particularly calcium fluoride, and also acid was known, hydrofluoric acid, but nobody had yet isolated fluorine. In fact, Uncle David here tried to do this, nearly killed himself. Other chemists did kill themselves trying to isolate fluorine. It is so reactive. Underneath fluorine we have chlorine. Chlorine is a toxic, poisonous gas. It gets its name from the greeny colour. So chloro here, chloros means greeny yellow. It's the same as you might have heard of chlorophyll. Well, it's not because it contains chlorine, it's because it means, well, greeny leaf, chlorophyll. So it's the colour there that gets its name. Bromine, bromine, one of my favourite elements. It's really evil looking. It's a liquid, a dark brown, orangey liquid. Gives off this vapor, really heavy, choking, horrible smell. In fact, its name, bromos, comes from the Greek meaning stinky or smelly. So that's how it gets its name. Right, iodine underneath gets its name from the beautiful violet colour of this substance. And this actually, iodine and chlorine were named by Humphrey Davy here in the Royal Institution. Acetylene, name for being stable there, and Tennessee from the state. So quite a nice one group. I thought I might show you one of these elements now, despite the fact that some of them are very, very toxic. I'm going to show you some iodine. And remember, this gets its name from this beautiful violet colour. So we're going to make some iodine. Now, at the back of the lecture, this is why we had to come in through the sides, I've got a very explosive compound. This is called nitrogen triiodine. And this compound has nitrogen bonded to iodine. But these are very, very weak bonds. And I'm hoping when I just touch this compound, not with my finger, as you shall see, but when I touch this, it should explode very violently. And this is because these weak nitrogen iodine bonds all rearrange during the explosion and form, well, the very, very strong bonds that we have in nitrogen molecules. So nitrogen, like the nitrogen that we breathe in, are molecules of nitrogen where two atoms are very strongly bonded together to form very stable molecules. And it's this that drives, I hope, will drive this explosion. It's the formation of the nitrogen gas. But we can't see the nitrogen gas that's going to be formed. It's invisible. I mean, it's in the air around us, of course, we can't see this. But we should be able to see the other byproduct of this reaction, which is the iodine. So you need to look very carefully, and you should see a purple cloud if it all goes well. Now, this reaction is a little bit loud, okay? And it is quite a sharp explosion. So I will be wearing these ear defenders, and this is always a good sign. When you see the lecturer wear ear defenders, you really do need to just cover your ears. Now, you won't need to stick your fingers in your ears, just put your hands over them, and this will stop the shock wave. Okay, which could, otherwise if you're close, particularly close, damage your ears. So just cover them. You don't need to cover them really tightly. Just put your hands over your ears. Okay, so let's give it a go. So let's put these on. Okay, and just check that everyone's got their ears covered. So just cover your ears. Okay, and there we are. Okay. So, I hope you saw the nice violet cloud. Seemed to have changed the screen a little bit. Never mind. So iodine is, of course, something that you will be familiar with. Maybe you've got some at home in a first aid box. There's tincture of iodine. So if you have a cut, you can use it as a disinfectant. So when you have the solution, it has this sort of browny color. This is the color that we'll see on the screen. That will actually disappear gradually during the course of the lecture. It'll probably be gone by the end of the lecture, which is quite interesting. Okay, anyway, so that's one of the elements from group 17. This group altogether, these similar chemical properties, are known as the halogens. And this word actually means the salt makers, because they're very easily readily formed salt. I mean, we know, for instance, that our common table salt, the proper name is exactly sodium chloride. And that is then made with some sodium from this side with the chlorine from that side. So these are all capable of forming salts. The group as a whole are known as the salt makers. Okay, now that's the halogens, group 17. Let's have a look at a couple of the noble gases. So where are you, noble gases? So very good. Okay, so these are all the noble gases. Now this is quite a remarkable group. Okay? This is the last group of elements to be discovered. None of these are in Mendeleev's table. Okay? Actually, the helium had been suggested, and sort of somebody thought there might be this strange element in the sun. Mendeleev thought he was mad, and so didn't include it, and had nowhere to include it in the periodic table. Anyway, this whole group was discovered after his table. The first of these elements to be discovered was argon. And it's actually the third most abundant gas in the atmosphere. Remarkable, okay? So the first most abundant is nitrogen, then oxygen, and then, well, it's not carbon dioxide, which some people think, it's actually argon. There's 1% argon in the atmosphere. And yet, people knew about nitrogen, people knew about oxygen for 100 years before they noticed the argon. And the reason for this, actually, is because it doesn't do anything. In fact, argon doesn't combine with any other element at all in the periodic table. Neither does helium, neither does neon. Okay? Some of the other ones just begin to. So some of krypton, xenon, radon, they have been made into compounds with some of the most reactive elements, such as our fluorine and maybe oxygen. But otherwise, these are very inert. And actually, this is what gave the name to argon. Argon comes from the Greek word argos, which is, of course, a well-known shop. Okay? And argos, well, I don't know, I presume they knew this when they named their shop. It means lazy or inactive, okay? Inert, okay, so not doing any work, so it's just an easy shop to do your shopping with. So this is because of this, the fact that it didn't react with anything else. It was a completely new element when it was discovered. Nothing like this had been seen before. Okay, so now remember, as we go down, all of these elements have similar properties. So all of our gases here have similar properties. They are all gases, as far as we know. We don't know about oganesson, since there are only about 5 atoms ever made anyway. But the rest of them are certainly all gases. And I have a balloon with, well, one of them here, and this is our helium. Okay, now, remarkably, I say these are so inert, okay, these even don't bond to each other. And this is quite remarkable. So whenever, with all of the other elements, so most of them are actually nice shiny metals, like this piece of an aircraft. I'm sure they won't miss it, it's just the turbine blade. This is actually made of titanium, but it's a solid, and this is because the atoms of titanium are all bonding to each other, okay, to form very, very high melting point solid here. But helium, none of these elements, in fact, do bond to each other, and they exist as individual atoms. And if ever you have a helium balloon, this is pretty much the only time you will ever come across individual atoms. So individual atoms in this balloon here. Okay, but as we see, they are lighter than air. Of course, helium is element number 2. It's only got 2 protons, 2 neutrons, and 2 electrons, so lighter than air. Well, I have some of the next element underneath it, some neon down here. So this is the element neon. Now, there's a rather remarkable thing, and that is that whenever we have equal volumes of gases, so these are clearly pretty much equal volumes, the same size, so long as they're at the same pressure and temperature, they actually end up containing equal numbers of particles. In this case, what it means is there is the same number of atoms of helium in here as we have atoms of neon in here. These are, of course, lighter than air. What about our neon? Well, it's probably the balloon itself that is sinking here. But remember, as we go down the group, we are increasing the number of protons, neutrons, and electrons, so each atom is getting heavier. Now, I can't have a balloon of oganesson because there are only 5 atoms, or 6 or so ever made, and it disappeared like that. Radon can't have a balloon full of that because it's very radioactive, so that wouldn't be good. The heaviest one that I can have is the xenon, and this is a balloon of xenon. Okay, so it's gone down a little bit over the course of the lectures, but pretty much the same number of atoms, maybe slightly less. We have it here and in here. But what about the mass of these? So it really is actually quite heavy, okay, for a gas. So I said it's the same number of atoms. So this really wouldn't be a very fun balloon to take to your parties. But this shows very nicely then that as we go down the group, what's happening, they're all still gases, but because we're increasing the number of protons, neutrons, and electrons, as we go from one period to the next, one row to the next, okay, the atoms themselves are getting heavier. Very important. Okay, well, thank you very much, noble gases. You've been very good holding your signs up. Thank you. Now, we mustn't forget the other elements in our periodic table. We have a lot in the middle, the dark blue cards. These are the so-called transition metals. Do you want to give us a wave, transition metals? So we have all sorts of things like titanium that we saw in the blade there. We have iron, copper, nickel, all sorts of nice, fun metals here. Gold, very beautiful, mercury there. Okay, so these are our transition metals. And then we also have the light grey. Now, you're right at the back there. So, yeah, I'm afraid that, rather important. Some of these are becoming more and more important now, such as neodymium. So we have our magnets containing those, very important, very strong magnets. But these elements here, they ought to be in the main body of the periodic table. So there's a little place marker there, the asterisk of the little cross, shows where they should go, these so-called lanthanides and actinides. But it would make the periodic table very long. So this is why we've put you out the way at the back there. Okay, but you ought to be in the main body of the periodic table. Okay, so these ought to be in there, but it would just make it very long, too long for the screen. Okay, so that's a brief overview of the elements of the periodic table. Now, what we want to do is look at the chemical properties of some of these. And we're going to start off with, well, the first two elements. And I think Chris has prepared a balloon of hydrogen for me and a balloon of helium, so we can compare these two. Okay, Chris, you seem to have used the same colour balloons. I think I deliberately told you to use different colours so I know which one's which. Okay, well, one of these apparently is filled with hydrogen, one of them is filled with helium. I have no idea which one's which. There is a difference between them. So remember, whichever one it is, the helium actually has individual atoms in here. The hydrogen, well, hydrogen forms molecules. Like, I mean, every other element in the periodic table, apart from the noble gases, they all stick to each other. Hydrogen forms molecules where two hydrogen atoms bond together. So one of these is filled with hydrogen molecules, one is filled with helium atoms. But actually, the hydrogen is still lighter. Okay? Hydrogen is the lightest element. But I don't know which one's which. So, oh dear, never mind. Anyway, but I do know a way to find out. We can use a test. A chemical test. Okay, I'm going to use my little candle here, my lighted splint, to see if I can see which one's which. So let's try this first balloon then. So it's either going to be hydrogen or it's going to be helium. You don't need to cover your ears unless you really, 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 really don't like any bangs at all. But otherwise you'll be fine. It should be fine, even if it is the really explosive one. We don't know. We'll see. Okay, well, let's give it a go. Now watch very carefully what happens with my flame. Okay, we'll see which one this is. Okay, so, well, all that happened there is, well, it actually made my flame go out. It didn't burst into flames. It must be the helium. So the helium, remember, is incredibly inert, unreactive. It does not react with the atmosphere. There's no explosion. All that happened was the balloon burst, and it even put my flame out. So it extinguishes flame because it doesn't do anything. Okay, it's completely inert. So that means we hope that this one, unless Chris has played a trick on me, they're both helium, we hope that this one is hydrogen. So let's try the hydrogen one then. So let's see if this is hydrogen. That was nice. So that was very nice then. They clearly have very different chemical properties. Our hydrogen molecules were explosive with the air, so they were combining with the oxygen. The helium didn't do anything whatsoever. So very different chemical properties, these two first elements. But of course, when the hydrogen does react, the flame that you saw there, it's the hydrogen gas there reacting with the oxygen from the air to form water, to form hydrogen oxide, H2O. Okay? And, well, hydrogen is first appreciated as an element by this chap here and his colleagues. This is Lavoisier, the French chemist. And he first drew up a list of elements, a modern list of elements. Unlike the Greeks, who thought, for instance, they have heard that they thought that things could be broken down into principles of gases like air, fire, earth, water. Well, he drew up, with his colleagues, the first list of elements in their modern forms. And it was in the book here, his traité published in 1789, and this is the English version from 1790. And here is the list. It's in the original French here. We're going to look at this in a little bit more detail. But one of the elements here, this is from the English version, is hydrogen. Okay, so he recognizes. In fact, he even gave it its name, hydrogen. And the name here derives from the Greek. Well, of course, I'm sure you know that so hydroelectric means electricity generated using water from a dam. So hydro means water. This means water maker, because as you just saw, our hydrogen easily reacts with the oxygen from the air to form water. So that's its unique property in the sense it can easily form water. It's the only element that can form water when it combines with oxygen. So Lavoisier named this because of that reaction. But there's a little bit wrong here, because two of the other so-called elements that are in his list, we've got light and what he's called caloric, which is heat. That's another word for that. And this is because he thought that these were also contained in different substances and they could be released, so they must therefore be there. Now, Lavoisier made some very, very careful measurements. He measured how much of one reagent combines with another during a chemical reaction. And this was one of the very, very important things. He measured how much hydrogen combines with oxygen, for instance. Okay, and this became very, very important later. And we're going to try this in a moment. And we'll also see why he thought that light and heat should be in the list of elements. I say we would not include them now. We know that they are forms of energy instead. Well, I have here some iron wool. Okay, this is very finely divided iron. And we're going to combine this with the oxygen from the air. So it's a chemical reaction. In a sense, we're going to be burning the iron wool here. We're going to be seeing how the mass changes. So I've set my balance here to be 0. We're going to see if it goes down, if it stays the same, or if it goes up. Okay, so we have 3 possibilities. So actually, maybe we'll have a vote. Okay, we'll have a vote to see who's right. So who thinks that the mass will stay the same? No one. Who thinks the mass is going to go down? There. Okay, got a few hands. Who thinks it's going to go up? Even more hands. I think if we had to ask the audience, we would say it's going to go up. Well, let's try it. We need to do the experiment. And this is the sort of thing that Lavoisier did. So, I'm just going to start the reaction. Actually, maybe we could have the lights down for this, perhaps. So I'm just going to start the reaction here. And you can see the beautiful light is being given out. And this is why Lavoisier thought that light is contained either in the iron or in the oxygen. He thought it was the oxygen. The mass has actually gone down. It's almost a gram heavier, lighter. So if you said it goes down, you were temporarily right, because it's going back up again. If anyone said it stays the same, well, it's almost back to where we started now. In fact, now it's back where we started. But actually now it's continuing to get heavier. So if you did say it's going to go heavier, you were quite right. Okay, now why is this? Well, say, you can certainly see the light, and I can feel the heat very nicely here. And it's probably this heat that's given out it decreases the density of the air that's trapped in here. That's probably why the mass went down initially, just as it became a little bit less dense, the air then. But it is actually going up. And why is this? Well, none of the iron has disappeared. It's still all there. However, it's now combined with the oxygen from the air. And so we haven't lost any iron. What we've actually done is gained some oxygen. We formed iron oxide. So the mass, of course, is heavier, because it still has the iron, and now it's also got oxygen built into this structure that we have here, this solid. So it's over 3 grams heavier now due to the combining mass of the oxygen that's now trapped into the solid. But the lighter heat given out, that's why Lavoisier included them in his list of elements. Also in his list, we see oxygen. He named the word oxygen as well, and azo. Well, that is the name that he gave to nitrogen gas. It comes from the Greek meaning no life, because it doesn't have life. It's a suffocating gas. We don't call it that any longer, and that's because actually pretty much every gas is poisonous and toxic or suffocating other than oxygen. So it's not a unique name. So this is why the name was eventually changed. But rather than using Lavoisier's list and go and look into that further, I'm going to use the list from another of my heroes from this time, and this was the chemist, well, the authoress, Jane Marson. She published a series of books that were really very, very good, and they got a lot of people excited and interested in science, in particular in chemistry. And so the book that I'm particularly interested in is Conversations on Chemistry. And this really did have quite a huge impact. It went through many, many editions, and this is why we're going to be looking at this, because we can see how her list of elements changes. Went through many editions, but it also got many people started on science. And actually one of the most famous people that got interested in science, thanks to her book, was a young bookbinder's apprentice. Okay, and this is Michael Faraday. Of all people. He probably should have been binding the book, but anyway, he was reading the book and doing a bit of experiments in here, and it got him excited, interested in science. He then approached Davy, made notes of his lecture, and got a job here, this building, okay, and he became one of Britain's most famous scientists. But it all started thanks to this lady. They became good friends throughout their lives, they corresponded with each other. She often came to this very room, attending his lectures to hear him talk about science, and then she would update her books with all the new science there. So absolutely fantastic. But let's have a look at her list of elements from the very first edition from 1806. Here it is. So it's very similar to Lavoisier's list. Also at the top we see light, air, oxygen, then nitrogen, hydrogen. So it starts off exactly the same. This is because, well, this is the list of elements. There are a few more elements in here than Lavoisier had, because it's a few years later, 20 years later. But there are some things that aren't elements, that are not elements, that are in both Lavoisier's list and in this list here. And these are, we see, potash and soda. Now I have some soda crystals here. I bought these from Sainsbury's, okay, and it's just washing soda. What this actually is just sodium carbonate. And it dissolves in water nicely, and I could use this to wash my clothes if I wanted. It's an alkaline solution. If I add some of this, it's a very dark green. This shows that it's a neutral solution. If I pour some in here, it goes to this beautiful blue, purple colour here to show that it's an alkaline, the opposite of an acid. Now, why is this in the list? Well, it's in the list because Lavoisier could not break down this substance. He could heat it up to very high temperatures and it would lose some carbon dioxide, but then it couldn't be broken down any further. They couldn't get the real elements out of this. So as far as Lavoisier was concerned, this was a simple substance that couldn't be broken down. He suspected that maybe there would be some element in here, but he couldn't get it. Similarly for the potash that's mentioned here, this is potassium carbonate. This couldn't be broken down either. Okay? We also have some other ones here, so it's lime, magnesium, strontium, barite. Well, again, these are substances that could not be broken down. The lime, what it actually is what you get if you try to break down by applying a strong heat some calcium carbonate. Now, calcium carbonate is chalk or it's a marble. Okay, so calcium carbonate, if you heat it up very strongly, what you end up with is lime. And I've got some here. Now we're going to look at this. It's quite an interesting substance. So this was included in Marseille's list of simple substances. It's quite hard. It's not hot. It's just lying around here. But it can do something really quite fun. And I need a volunteer. Your hand went up very quickly in the grey. Do you want to come down, please? Okay. Right. Now. Okay. Very good. Thank you. And you might need to see if you can put those over your goggles. So extra goggles, this is good. Extra ones. Now get a tiny little watering can there if you don't want to pick up that to spill it into the water. And what I'd like you to do is to pour water over this, just flood this, and then just step back a bit, just over to there. Okay, thank you very much. So you can just pour water all over, give it a good flooding all over both pieces. That's good. That's very good. Okay, and just step back. Thank you. Okay, so far now it was cold, the water was cold, and violent reactions take place. In fact, this reaction is so violent that this is steam being given off. And the reason I had to ask you just to step back is because actually little bits can ping off of this sometimes. It really just depends. So now it's much flakier. I'll add a bit more just to there. So the substance is lime. The lime is sometimes also used for calcium carbonate itself, but this substance really is also known as quick lime. And the quick here doesn't mean it's fast, because it isn't really very fast. Quick is an old word meaning living. So, for instance, quicksilver means living silver, mercury. We have the quick part, as the living tissue. Okay, there's a phrase for quick and the dead. It doesn't mean the living. Fast. It doesn't mean the fast-moving and dead people. It means the living and the dead. So this is a living rock, this living lime here. Okay, very, very violently reacts with water. I think a round of applause there. Shall I take your goggles there? Thank you. The chemical reaction taking place there, the calcium oxide we have reacts with water and it forms calcium hydroxide. This doesn't dissolve very much in water. This is sometimes called an earth. It does give an alkaline solution. These were eventually called alkaline earths. Okay, but they couldn't be broken down any further at the time. So they were simple substances. They were, as far as the Lavoisier is concerned, elements, simple substances. But then what happened? Somebody did actually manage to isolate some elements, not only from this, also from our soda. And this was Humphrey Davy here in this very building. Okay, he isolated from the soda. He isolated a new metal that he called sodium because it was in the soda. From this substance here, he isolated a metal that he called calcium. Okay, now so these elements now appear in the next edition of Marseille's book. Okay, so these new metals that really are elements, they feature in it. But she needed a way of trying to classify this, because this is some 50 years or so, more, 60 years before the first periodic table. So this list is getting quite long of elements. And she thought, well, how can I divide it unsensibly? So what she wanted to do is to classify things about how they react with oxygen. Okay, so because most of the elements, almost everything, of course the noble gases weren't known at this time, almost everything combines with oxygen. So this was a nice, convenient way to classify the elements and how they react with oxygen. So in the second edition, third edition, she says here, these are metallic bodies that form alkaloids. So this is now the metal potassium that forms potash and sodium that forms sodium. So these are the metals that are newly isolated. We should look at these in a moment. Okay, we also have the metal calcium that forms our calcium oxide here. Initially, Davy, when he first isolated these and wrote the names, he named magnesium. He called it magnium for various reasons. Eventually, this became magnesium. So these are the new metals that were isolated. Now, this idea of how the elements react with oxygen is something that also Mendeleev picked up in his periodic table. So remember, the very first one was published in 1865. This was in the first volume of his textbook. Well, in that one, actually, the groups of similar elements went horizontally across the page. In the next version that he put together 2 years later, which came in volume 2 of his textbook, he now has the groups of similar elements going vertically. But what I wanted to draw attention to is what's right at the top there. He calls these vertical arranged groups elements. It's in Russian. It says Grupa 1, 2, 3, and so on. But he also gives these generalized formulas for how the formula of the compounds when they react with oxygen. Now, So the general formula, we have 2 atoms of the element, 1 atom of oxygen, then 1 to 1, or as he writes here, 2 atoms of the element, 2 atoms of the oxygen, and so on. So there are these different trends as we move across the periodic table. So according to how they react with oxygen, this is what we're going to look at now. So we'll start off with group 1. In fact, we've already seen one of the elements and how it reacts with oxygen. This is, of course, the element hydrogen. And we know the formula of what we get. When hydrogen reacts with oxygen, we get H2O. So 2 atoms of the element, 2 atoms of hydrogen, combined with 1 of oxygen. But it isn't just hydrogen that this is the case. Other elements can also form similar compounds with similar formulae. I'm going to show now the reaction of lithium. So Chris here is just putting some oxygen into the gas jar. And I'm going to take a little piece of lithium. So this is lithium foil. So I can easily cut this with the scissors here. I'm going to cut a little piece of foil. Actually, I'll take a little snip, another little snip off there. And use it at the moment for a different direction. Excuse me, I'm going to put my lithium on this. Well, this is called a deflagrating spoon. It's meant to have a spoon on the bottom. This one doesn't, but never mind. Anyway, you'll see why in a moment. So I'm just going to put this, hang this on the bottom here. So that's my lithium wrapped around the bottom there. So we've got oxygen in the jar, and I'm just going to get this burning. Now, lithium compounds, when they're introduced into flame, often give a really nice, brilliant red color. So you may see a little bit of red color, but then hopefully you'll see the chemical reaction taking place. So an incredibly vigorous reaction taking place there. In fact, this one is so vigorous that it's actually now the iron that's burning in the oxygen there. That glowing thing is the iron, and the end of the iron has just fallen off, and my rod has got much smaller. I shall give that to Chris, thank you. But the formula of the oxide that we're making is Li2O. So like H2O, we have Li2O. So 2 atoms of lithium with 1 of the oxygen there. Okay, if I dissolved some of that smoke in water, it is also an alkali. It easily dissolves. It's the opposite of an acid. But I can make that same alkali by reacting some of the lithium metal with water. And this is what I shall show you now. So remember, I snipped off an extra little piece here. So I'm just going to add this to the water. And we can see some interesting things. So let's add this to the water. There it is. Now, remarkably, this floats on the surface of the water. And this is because, well, this is element number 3. It's only got 3 protons, 3 electrons, and some neutrons. It's actually light enough, less dense than the water, it floats on top. But it doesn't mean to say it would make a good material to make a boat out of, because, well, actually, it's now disappeared. It's reacting with water to form lithium hydroxide. Okay, so we form lithium hydroxide and hydrogen gas. Okay, completely disappeared. Well, actually, it's not just lithium that does this. Some of the other elements do. These also react with water to form alkalis, potassium and sodium. Lithium isn't in this list because it hadn't been discovered when Marseille wrote this edition of the book. Let's try the next element underneath lithium, and this is the element sodium. So we're going to try some sodium with water. So I'm just going to take a tiny little piece here of sodium and add this to the water. I hope. There it is. And it's actually fizzing around on the surface of the water. Oh, there's a little flash of flame there. This is a remarkable substance. I mean, nothing like this had ever been seen before. When Davy first isolated this here, he thought, is this even really a metal? Metals aren't lighter than water. They shouldn't float. They don't react with water like this. This was something that had never been seen.
Thank you. I don't know if you've wandered around the Royal Institution here, but you notice that on various walls there are video screens showing a kind of greatest hits clip show. You get to see David Attenborough and others with animals doing fiercely clever things right here at this desk, and others are doing demonstrations with extremes of high and low temperature, or a Rube Goldberg machine with a marble running down. And I'm watching this before my own lecture, and I'm thinking, you know, those poor audience members forced to sit through all this mummery when what they really want are some good old equations. You have come to the right lecture. We all know the importance of equations in physics, and we also know that they're treated as kind of scary. You're not supposed to tell people about them. Stephen Hawking says every equation cuts your book sales in half. My publisher didn't like that idea, but there's also a level of appreciation and understanding you get when faced with a good equation. Here is a famous equation. This is an equation that we all know was given to us by Albert Einstein. E equals mc squared. The energy of an object just sitting there is equal to the mass of the object times the speed of light squared. It's almost an icon of inscrutability, but it's actually not that hard to understand. It's, you know, a little multiplication. There is a superscript exponent for the 2, but that's okay. We know how to square a number. It's not really that hard. It's also not what physicists think of when they say the phrase Einstein's equation. Here is Einstein's equation, as physicists think about it. This equation is the dynamical equation telling us how the curvature of space-time responds to energy and mass and momentum in the universe. If you were to say it out loud, r mu nu minus 1/2 r d mu nu equals 8 pi g t mu nu. We never show you this equation. You don't see this one for obvious reasons. It seems very intimidating, doesn't it? There's all these symbols. Some of them are big, some of them are small, some of them are Greek. And it seems like it would be an effort to explain it to people. But I'm trying to imagine that maybe the effort is a little bit worth it, at least at some level. You know, an equation is often related to a poem in some sense. And it's actually very similar. Equations are short, and they are powerful, and they are precise. Every little bit counts. Every little notation, every little dash, etc. means something. And it is a little bit of work to dig into what those symbols mean, but it's very doable work. We have 58 minutes left. We're going to do it. And I think it's worth doing it because, you know, I'm not going to give you homework unless you really want some. I have good homework available, but the point is that if you understand the equation, you appreciate the science at another level that you wouldn't otherwise do. So it's worth the effort to at least think about it. What I'm hiding from you is that it's also kind of fun. I think that it's not just a matter of effort. You'll see this and you'll say, like, why did they always hide it from me for all those years? So we'll start gradually, okay, with the idea of classical mechanics. Sir Isaac Newton, a famous English person, gave us classical mechanics in the 17th century, and it really boils down at the end of the day to a single equation, F equals ma. There is a little bit of intimidating factor here because the F and the A have little arrows over them. That's because they're vectors. What this equation means is that the force that acts on an object is proportional to its acceleration, how fast it starts moving, the rate at which it starts moving, and the constant proportionality is, once again, its mass, m. Force equals mass times acceleration. This seems straightforward enough. It was a big deal at the time because it used to be thought that nothing could move at a constant velocity forever unless you kept pushing it. And Newton comes along and says, no, no, no. If you don't push something, that's exactly when things move at a constant velocity. It's friction and so forth that slow them down. So what is so great about this equation? Why is it such a big deal? Well, it's both precise and it's everywhere. By precise, we mean it's not just a suggestion, right? It's not saying, well, you know, the more you push, the faster things go. That's true so far as it goes. But this is numerical and quantitative and precise, and if you want to fly a rocket to the moon, you're going to need to know exactly how much fuel you need. This kind of equation takes that into consideration. But the everywhere-ness is even more important. This equation doesn't say that one time that I pushed my car, I acted a force on it and accelerated a little bit. It says every time anybody in the history of the universe pushes a car, or anything else, the force that they exert on it will be proportional to the acceleration. That's really why the equations are so great, because they give you, even though you're just sitting here thinking about it in this room right now, suddenly you have an insight into the workings of the whole entire universe throughout its entire history, if things go well. That's why it's worth kind of contemplating what's going on here. It also doesn't tell you anything until you tell me what the force is. How much force am I putting on things? Well, here's another famous equation, also from Sir Isaac. The story of him sitting under the tree and having the apple fall on his head is probably apocryphal, and certainly was promulgated by Newton himself, who thought it kind of burnished his reputation a little bit as an inscrutable genius. When the apple fell from the tree, the point is not that Newton discovered gravity. Guess what? Even before Newton, we knew that there was something called gravity. What Newton realized is that universality, that everywhere-ness of gravity. The fact that his inspiration was that the apple falling from the tree is explained by the same set of rules that explains the planets moving around the sun, etc. The rules apply everywhere. And in this case, the rule is that the force due to gravity is inversely proportional to the distance between two objects. So if we have a heavy object, capital M, light object, little m, we make another little vector called E, which is just the directionality of where the force is pointing. It goes from little thing to big thing. And the force is the mass of the big object times the mass of little objects divided by the distance between them squared times a constant, capital G, which we call Newton's constant for obvious reasons. And this pair of equations, F equals ma and F equals gmm over r squared times the unit vector, they make the universe go, or at least we thought they made the universe go until Professor Einstein came along. They did a pretty good job. If you want to get a rocket to the moon, you don't need to know about Einstein's equation. You definitely need to know about Newton's. And already, well before Einstein, there's a really important implication of this, which is going to be important later on in the talk, but it's also showing you some of the power of thinking in terms of equations. Because if the force that you act on something is the mass times acceleration, and the force acting on something is the mass of the other thing acting on it times Newton's constant times its own mass divided by r squared, then the masses cancel out. You can divide by little m. There, we just did some math. Pause to congratulate ourselves for doing some math. We divided by little m on both sides. And you instantly learn something profound and counterintuitive about nature. The acceleration due to gravity that acts on an object doesn't care how heavy that object is. This seems counterintuitive. If I take a hammer and a feather and I drop them, they will drop at different rates. And in my brain, I think that's because the hammer is heavier. So here is an artist's impression of a experiment that was actually done by the Apollo astronauts. They took a hammer and a feather up there, they dropped it. They had very bad video cameras for some reason, so this is a painting remembering the event, but the point is, on the moon, the hammer and the feather fall at the same rate. The real reason the hammer and the feather on Earth do not fall at the same rate is because of air resistance, clearly. But this is a crucially important insight into how gravity works. Because again, it's everywhere, it's universal. All objects accelerate under the same way, the same rate, under the force of gravity. Gravity is the universal force. Keep that in mind. It's going to be on the test. It's going to be coming up later. And you know, for centuries, classical mechanics was so successful that people thought they had figured out the basic framework according to which the universe works. And it was just a matter of getting, all right, what are the forces, what are the things acting, we'll put it into this framework that we have. But then, the 20th century comes along. Quantum mechanics, that will be book 2, by the way. So I'll be back here, we'll be talking about quantum mechanics later, but the other thing that happened is relativity. And relativity came in 2 pieces. One is special relativity in 1905. It's good occasionally in science talks to see photographs of Albert Einstein when he was young, when he was thinking up all this stuff. You know, he kind of went to seed later on. He looks avuncular. Here, he looks like the smartest guy in the world. He looks smarter than you, right? Like, you would talk to him and you would feel intimidated. Someone was combing his hair. And special relativity, there's a list of things going on about the speed of light, time dilation. It's all wonderful. We're not going to get into it. The book gets into it. Read the book, but we don't have time for that right now. What I want to do is simply use it as a springboard to general relativity. General relativity was where Einstein really became a celebrity. In a very real sense, special relativity was Einstein was in the right place at the right time, and he put a sort of capstone, put things together that other people had already been working on. General relativity was his baby, but he kind of got there reluctantly, because this is 1905 special relativity. In 1907, Hermann Minkowski, who had been Einstein's math professor, says, you know, your math professors read your famous scientific papers, and Minkowski said, I have a better way of thinking about this. When you talk about special relativity and time dilation and all that stuff, it's more mathematically elegant to imagine that what's going on really is that you have unified space and time. And he has a quote, henceforth space by itself and time by itself are doomed to fade away to mere shadows, and only a kind of union of the two will preserve an independent reality. He made very poetic scientists back in those days. People were, you know, skeptical, actually. They were not immediately impressed. One person who was skeptical, Albert Einstein. He says to his old professor, Minkowski's formulation makes rather great demands on the reader in its mathematical aspects. So if you're ever reading something and you're like, the math is too hard here, imagine that you're Einstein and you think, the math is too hard here, I'm not going to bother. As good as Einstein was, in fact, I would argue that in some sense he's underrated as a physicist. But he was a physicist at heart. He was not a mathematician. He didn't love math for its own sake. He learned exactly as much math as he needed to know, and no more than that. So he looks at Minkowski's work and he says, okay, you're doing some formalism, it's all very elegant. It doesn't really do me any good. I'm a down-to-earth kind of guy. I want to imagine people going at the speed of light, things like that. But why did Minkowski think this? Because guess what? Einstein was totally wrong, and he's going to change his mind very quickly. It's the geometry of space-time that really makes it an interesting thing to think about, rather than space and time separately. Think about what we mean by the geometry of space. There's a lot going on in the geometry of space. We're imagining here good old Euclidean geometry, the geometry of the tabletop. And it's useful to us. For example, if you have coordinates, if you have an X and Y coordinate system on the tabletop or on the city or whatever, you can use that to figure out how far you've gone. This is a typical geometry problem. You can invoke Pythagoras' theorem, right? If you're moving on a straight line, but it's diagonal compared to the x-axis and y-axis, the distance you travel is going to be the square root of x squared plus y squared, okay? The hypotenuse squared is the other two sides squared, their sum. That's something that you might use when you have, the guy is supposed to have a little odometer here, counting his steps, figuring out how far he's gone. So it's a practical, kind of down-to-earth thing. What Minkowski says is that you can think about Einstein's special relativity as exactly the same kind of thing, but replace distance traveled with time elapsed. So before Einstein and Minkowski come along, time was this universal thing, according to Newton. Everyone agrees on what time is. Not everyone agrees on the distance you travel. That depends on the path you take, right? Between 2 points, you can go in a straight line, you can go in curvy lines, different distances. But time you thought was universal. Minkowski says no. What you have to do is use Pythagoras' theorem for space-time, which involves a little trick, namely a minus sign. So Minkowski says that the elapsed time between two events in space-time can also be calculated in terms of a coordinate system, but now your coordinates are x, y, z on space and t in the time direction. And there's a difference between t, the universal time coordinate on all of the world, versus tau, what we call the proper time, what you actually experience, what you actually measure on your wristwatch. And there's a formula for it, and it looks very much like Pythagoras' theorem, but not quite. Pythagoras says d squared is x squared plus y squared. Minkowski says the time you measure squared is t squared minus x squared. If you've ever tried to wonder which twin it was that aged more in the twin paradox, because I know I've had to wonder, just remember this equation. The minus sign means the more you travel in space, the less time you are going to feel elapsing. That is a brilliant codification of all of the ideas of special relativity right there. So, meanwhile, while Minkowski was saying all these mathematical niceties, Einstein was worried about gravity. When we talked about classical mechanics, the first thing we did is say, okay, let's imagine a specific force of nature, gravity. It all worked out very nicely in the Principia Mathematica. Newton told us both the rules of classical mechanics and his inverse square law for gravity. So Einstein very naturally figured he had special relativity replacing classical mechanics. Now he needs to replace Newtonian gravity. It didn't work. There's sort of an obvious set of guesses you go through as a theoretical physicist. None of them work. You need to come up with something a little more profound. So Einstein hit on something called the principle of equivalence. Remember, even Newton had figured out that gravity is a universal force. Drop two things, they will fall at the same rate, no matter what their mass is, but also no matter what they're made of, no matter what time of day it is, and so on. So Einstein puts this into thought experiment form. He was the best thought experimenter in history. And he says, what this means is, in some way, gravity isn't really a force at all. Because I can't tell if I'm in a gravitational field. I can sit here and I can do experiments. I can drop things and they will fall, and I will say, aha, gravity made something fall. But he says, I would say exactly the same thing if the Earth had disappeared and this whole lecture hall was in a rocket ship, accelerating upward at 1g. That hasn't happened. Do not be alarmed. But Einstein says there's no experiment you can do as long as we're locked in the lecture hall that would tell the difference. Gravity and acceleration are indistinguishable from each other. Now you and I, that's the principle of equivalence, and you and I would say, aren't we clever for having thought of that equivalence? And then we move on with our lives, but Einstein was Einstein, and he's like, this means something. I got to be able to use this to come up with the right way to marry relativity and gravity. And he suspected that what he needed was more math. And he wasn't very good at math, like I said. He was good at it when he needed to be. He didn't do it for his spare time, though. Happily, one of his friends from graduate school, Marcel Grossmann, was an expert in what at that time was the fanciest mathematics and geometry out there. Here's Grossmann on the left. And so Einstein says, Marcel, you got to help me with this. And Marcel Grossmann taught Einstein what at that time was the most modern ideas in geometry. So what does that mean? What counts as a modern idea in geometry? Well, Euclidean geometry, which we talked about with Pythagoras' theorem, is based, as you might know, on a set of axioms, and the famously weird axiom is the parallel postulate. The idea that if you start with a little line segment, take two perpendicular rays and let them move off to infinity, Euclid says they will stay exactly parallel at the same distance forever. For many years, for literally centuries, millennia, I suppose, people tried to prove this feature of geometry based on Euclid's other axioms. When I was in high school, our geometry teacher gave this to us as an extra credit assignment to prove the parallel postulate. He was very cruel because you cannot prove the parallel postulate, as they realized in the 1830s, because you can replace it with other perfectly good postulates. You can say either that those initially parallel lines converge at a constant rate, or maybe they diverge at a constant rate, and you get perfectly good theories of geometry, different than Euclidean geometry, but perfectly good in their own right. If the lines start to converge at a constant rate, you get spherical or positively curved geometry. If they diverge at a constant rate, you get a saddle or hyperbolic or negatively curved geometry. And these were investigated, and they were just as good as Euclidean geometry. So people started to say, well, why does Euclidean geometry work so well in the world? What's going on? Other people said, we're still making an assumption here. The assumption we're making is that if those lines start to converge or to diverge, they do so at a constant rate. It was Gauss, Carl Friedrich Gauss, one of the greatest mathematicians in history, who said, look, once you tell me that I can have a sphere or a saddle or a potato chip, I can have any wild thing that I want. I could even have a 3-dimensional space, or a 4-dimensional, or a 29-dimensional space. And they could be diverging some places, these lines, and converging other places. Like there's suddenly an infinite number of geometries that I could think about. Happily for Gauss, he had a very talented graduate student, Bernhard Riemann. And Riemann was already a well-known mathematician, but in the German system, there's a never-ending series of exams you have to pass before you can become a professor. And so the last one, the habilitation exam, Riemann gave Gauss a list of possible topics that he could study, and Gauss pointed to the one that Riemann thought was the most boring, the foundations of geometry. Do that one. Riemann goes off, and it's hilarious to read this. I did this, for writing the book, but the first time I actually looked at Riemann's paper, and he can't stop kvetching within the paper. He's like, I don't like doing this, but, I'm told to do this. It's not my natural métier. Riemann's purpose was to figure out how to, in absolute perfect generality, capture the geometric structures of a space in any number of dimensions without embedding it in any other space, just its own intrinsic character. So that's obviously a lot of ways that space could curve or twist or bend or whatever. What is the simplest way to distill that down to some usable information? And Riemann, because he was quite clever, he figured out that if you know the length of every curve that you can draw, so imagine on this tabletop you just draw every single curve, both straight lines and curved lines and everything. If you had the information in your brain about the length of every curve, that would completely fix the geometry of the space. The only way that those curves can fit together is if the space is flat. Or in this picture, these are spheres with little balls of yarn, little lines crossing on them. Riemann's insight is that all you need to know is the length of every possible curve that fixes the geometry of the space. How does it work? It's kind of like Pythagoras' theorem again, but because things are arbitrarily twisty, you zoom in. For those of you who know calculus, this is the traditional calculus trick. When things are curvy and changing, you zoom in, and if you zoom in carefully enough, everything looks straight and flat and constant. So Riemann says, I can take some arbitrary twisty curve, I can zoom in on it, and I can use Pythagoras' theorem. So in this case, this little 3-dimensional diagram, the length of a tiny little line segment is x squared plus y squared plus z squared, the square root of that. So Riemann's self-appointed task is, let's generalize this. The nice thing about this picture we drew is that it's actually in flat space. So I've drawn coordinates x, y, z. If the space is not flat, if I'm on a sphere or a torus or something crazy, I might not be able to use such convenient coordinates as x, y, and z. And in fact, what happens is when your coordinates begin to get a little bendy and curved themselves, the formulas begin to look a little bit more elaborate and less intuitive. So this may or may not mean anything to you. This is just for those of you who are familiar with the idea of spherical coordinates. So you have x, y, z, but you could also just say, what is the distance to the point? What is the angle from some line of longitude? Or what is the angle from the North Pole? That gives you spherical coordinates, which are very useful when you have spherical symmetry. And here is the formula for the distance of a little infinitesimal line in terms of r, the distance, theta and phi, those two angles. No information about that particular equation needs to penetrate into your brain other than the equation becomes more complicated when the situation becomes more complicated. So what Riemann needs is, what is the maximal complication? What is the most arbitrary way that we can think about this. You stare at this expression, you ask what is going on, and if you're Riemann anyway, you say, okay, I think what's going on is that I have on the left-hand side some interval. I would like to say some distance, but in space-time, it's going to be some time. So we use the word interval to mean either space or time. Some interval squared is on the left-hand side. That's what we inherit from Pythagoras. On the right, we have a sum of terms with all the different coordinates times some number, some quantity, right? So dr squared all by itself, but then the theta squared term has an r squared outside, phi squared has r squared. Like, there's a whole bunch of things going on. The general pattern is some number times a coordinate times the other coordinate. So coordinate squared times some number. In other words, in space-time, for example, where you have t, x, y, and z, you're going to have a formula for the interval in space-time, just like Minkowski gave us, but maybe more general. So the interval squared is going to have some number times t squared, plus some number times t times x, plus some number times t times y. If you have 4 dimensions, t, x, y, z, there's going to be 16 terms. 4 times 4 is 16, right? T, tx, ty, tz. You can go through them all at home, or right now, in your head, if you're that good. It quickly becomes unwieldy, right? Too many terms you have to write out, it becomes boring. If there's one thing that mathematicians are very, very good at, it is inventing notation that makes unwieldy but understandable things into very elegant but impenetrable things. So they do that. They invent something called the metric tensor. And the first step here is to relabel your coordinates. You thought you were happy with t, x, y, z, coordinates on space-time, but someone reminds you, you might use spherical coordinates or something more complicated. So rather than t, x, y, z, let's call them x0, x1, x2, x3. Immediately someone says, why did you start numbering with 0? Well, it's because physicists, bless their hearts, like to imagine more or fewer numbers of spatial dimensions, right? Maybe only 2 spatial dimensions, maybe 9 spatial dimensions if you're a string theorist, but we only always have 1 time dimension. So give time the label x0, and all the spatial dimensions are x1, x2, x3, etc. And then the whole shebang, you call it x mu. So mu, the Greek letter mu, is an index that runs 0, 1, 2, 3. Or if you want, t, x, y, z. Completely equivalent. x0 is time, x1 is x, and so forth. That's where the mu is coming from. Remember the mu? The mu's in the news from Einstein's equation, right on the second slide there? Here's where they come in. They are labels on directions you can move in space-time. T, x, y, z. So it's not really that new and crazy. And then rather than saying some number times t squared plus some number times tx, invent a new notation, g mu nu. And g mu nu is simply the number that gets multiplied by x mu x nu in that equation. So the interval squared in perfect generality is g00 times x0 squared, g01 times x0 x1, and so on. We have not yet achieved perfect inscrutability or compactness, so this is just the sum over all those values the indices take of g mu nu times x mu times x nu. That big sigma is another Greek letter. It means you sum over all the different possibilities. So these two expressions are exactly the same thing. This little purple thing, sum over mu and nu, g mu x nu, is just g00 x0 squared plus g0, etc. Okay? Now onto the stage comes Albert Einstein, who, as you might imagine, was doing his homework for Marcel Grossman, trying to teach him geometry, and he goes, this is very tiring, writing all these summation signs. I'm going to invent a new notation in which you write the same thing, but you don't write the summation sign. He was so proud of himself. He literally was telling jokes. He said, I've made a great discovery in mathematics. You don't need to write the summation sign. As long as you have repeated indices, you imagine that we mean you should be summing over them. It's called the Einstein summation convention. Not the most important thing Einstein ever did, but he got a kick out of it. Now we have reached full inscrutability. It's very compact. G mu nu x mu nu x nu. I'm even leaving out some of the complications because I like you. But this is, you see what's going on. We've taken the question, how do we generalize an arbitrary geometry? Well, you know the length of every curve. How do you encode that information? Here's how you encode that information in the values of the components G mu nu. Let's see that at work, okay? So G mu nu is the metric tensor. We've already secretly seen it. When Minkowski told us about space-time, he said that the time interval you measure, tau, is related to the coordinates t, x, y, z by tau equals t squared minus x squared minus y squared minus z squared. In terms of that little formula we had on the previous slide, that means that G mu nu is usually 0, right? There's no term in the equation that is x times y, for example. That's why you get all the zeros on the right here. But in principle, the rest of them you can read off. The G00 or GTT is +1, GXX or G11 is -1, and so on. And furthermore, all of these symbols have meaning. I mean, you knew that they did, but we can even tell you what the meaning is. The spatial ones, the X's, Y's, and Z's all by themselves, not involving T, those really are just the generalization of Pythagoras' theorem, maybe in a curved spatial geometry. Those are the spatial distances. GTT, what is that doing? It's telling you how fast time flows. Now that's an entirely preposterous idea, how fast time flows, because time flows at 1 second per second. There's no other rate at which time will never flow at 2 seconds per second, okay? But the time that you experience tau can flow at different rates with respect to the time coordinate. The time coordinate is nothing physical, it's just something that we use as a convenience. So GTT, that component of the metric, tells you how fast time flows compared to the coordinate that everyone has agreed to use. And then the ones that mix space and time literally tell you how time and space can twist into each other. Now, we don't have any of that in the Minkowski metric. That's not going on. You might say, like, when is time and space going to twist into each other? When will I ever see a major Hollywood blockbuster in which that happens? Well, you have, because time and space twist into each other when you are close to a rotating black hole. This is a famous image from Interstellar, right? The movie. This is the black hole, Gargantua. And all of the image here, all of the little filaments of light, were calculated numerically by using a metric tensor which had significant rotation, twisting of time and space into each other. It was so much work that Kip Thorne, Caltech Nobel Prize winner, who is also the executive producer and inspiration behind Interstellar, collaborated with the special effects folks here in the UK to write a paper. I mean, they also made a movie, but they wrote a paper, more importantly, in classical and quantum gravity, where they explained all the mathematical details that go into making this picture. And if it weren't for the components of the metric tensor that let time and space bend into each other, it couldn't have happened. I hope you enjoyed that little pop cultural interlude, because that's it. No more of that. Getting serious once again. Okay. So Einstein is taught that Riemann figured out how to capture the information you need to characterize a perfectly arbitrary curved geometry. Now you need to put it to work. How do you make money out of this metric tensor? Because what you care about is not the distance along a curve. What you care about is the curvature of space-time. What does that mean? Well, if Euclid says that you start with two initially parallel lines and they stay perfectly parallel, and Euclidean geometry is flat geometry, then curved geometry is not flat geometry. Curvature is all of the different ways in which those initially parallel lines can fail to be perfectly parallel forever. So we have a way of characterizing this called the Riemann tensor, much better than the metric tensor, because the metric tensor only has 2 Greek indices. A Riemann tensor has 4 Greek indices. That's twice as many. And the game that you play is, you tell me what point you start with, what line segment you start with, what direction your initially parallel lines go at. You ask the Riemann tensor the question, what happens to them as I extend those lines? And the Riemann tensor tells you how they twist around or converge or diverge or whatever. So the Riemann tensor is really capturing what you care about in the geometry. That is to say, it's curvature. The G mu nu is the raw data, the metric tensor, but what you want is the Riemann tensor. So just to get this, in context here, we've seen secretly different kinds of tensors, different kinds of quantities that are geometric and have different numbers of components. A momentum in space-time. In ordinary Newtonian mechanics, momentum is a three-dimensional vector, but guess what? In space-time, it's four-dimensional because you have a time-like component as well. You've seen the metric tensor, 4 by 4, so 16 components. The Riemann tensor has 4 indices, so it is a 4 by 4 matrix of 4 by 4 matrices. And I swear if anyone says they see a typo in this, I'm going to smack them. Again, this is one of those slides you're not supposed to get any knowledge out of it. You're just supposed to be impressed and go, wow, there's a lot of Riemann tensor out there, okay? And if you're a graduate student in physics, in my day, you would calculate the Riemann tensor. These days, they have their fancy computers and everything, and they don't know what that's like. So this was a lot, so let me just capture what you're supposed to take away from this, okay? The geometry of space-time is what you need to talk about in general relativity. This is Einstein's insight. If gravity is a universal phenomenon, then it is not like electromagnetism or other forces. It is a feature of space-time itself. What feature is it? It's the geometry of space-time. He needed the math to describe that. He was taught it. It's Riemannian geometry or differential geometry. That can be arbitrarily complicated, but Riemann let us whittle it down to a little usable piece of information. How to calculate the length of every infinitesimal curve, and from that you can build up the geometry as a whole. That information, in turn, is captured in the metric tensor, 4 by 4 tensor in 4 space-time dimensions, and that tensor has a curvature characterized by the Riemann tensor. So in other words, the metric tensor and the Riemann tensor aren't completely separate. The whole point of the metric tensor is it tells you everything you need to know as long as you can extract it. So the Riemann tensor is defined in terms of the metric tensor. If you're a working general relativist, your day job is usually figuring out either the Riemann tensor from the metric tensor or some vice versa kind of version of that. The next question, if you're Einstein, is how are you going to use that technology to come up with a physical theory, a theory of gravity? Well, you knew what Newton did. Remember, this was not just showing off when we talked about this before. This is Newton's way of telling you the acceleration due to gravity, right? The acceleration depends on Newton's constant times the mass of the Earth or whatever it is causing the gravity, divided by the distance between you and the Earth squared, the center of the Earth in this case. So Einstein needs to replace both sides of this equation. The left side, the acceleration due to gravity, he needs to have some measure of the curvature of space-time. On the right-hand side, the source of gravity. For Newton, the source is the mass of the gravitating object. What's it going to be for Einstein in this relativistic context? You already know it's not just going to be the mass, because Einstein told you that E equals mc squared, which is a hint that energy and mass are somehow unified. They're somehow part of the same thing. So mass is not the primarily important thing that it was for Newton. In relativity, mass and energy and heat and momentum and strain and pressure, all of these things are somehow going to be sources for gravity. What we need, I should ask if anyone can guess. Do you know what we need? We need a tensor. And we have one. I didn't give you time to guess. Sorry about that. I didn't want to be shown up by someone actually guessing. So the energy momentum tensor is basically another 4 by 4 matrix that tells you all of those things. It's called T mu nu, and it encapsulates all of the different forms that energy and momentum and other related quantities can take. And once again, we can look at it component by component. There's a 0,0 component, or TT component, if you like. That tells you the energy, including the mass. That's what we usually think of as the amount of energy in the good old Newtonian sense. These diagonal components, Tx, X, Y, Y, Z, Z, that's the pressure. So we're thinking here not just of a single object like Newton would have thought of, we're thinking of maybe a fluid or a solid. So you take some little region of it and there's pressure in the X direction, the Y direction, the Z direction. Those different directions are the diagonal components of the energy momentum. Then there are off-diagonal components which you can sometimes ignore, not always, but they tell you about how energy is changing and moving from place to place, the heat flow, the momentum, and so forth, okay? So all together, all the different ways you can think about energy are bundled up in this tensor. This is definitely going to be something we're going to use as we construct the new equation for gravity that Einstein is looking for. We have the metric. The metric defines the Riemann tensor, which characterizes the curvature of space-time. Mass is a kind of energy, so we're beginning to see left-hand side and right-hand side come together. We want to replace Newton's equation, okay? There's an obvious guess that it's not going to last very long. On the left-hand side, acceleration maybe should be replaced by the curvature of space-time, which is, as we know, characterized by the Riemann tensor, r lambda rho mu nu. And the right-hand side of the equation, which has the mass in it in Newton's equation, should have the energy momentum tensor, t mu nu. So we have curvature of space-time on the left, stuff, energy, momentum, and mass, and so forth on the right. Obviously doesn't work. I can just imagine Einstein going like, so close. It didn't work. It doesn't work because the Riemann tensor is a 4x4 matrix of 4x4 matrices. The energy momentum tensor is a 4x4 matrix of numbers. They don't match up. They can't be proportional to each other. Fortunately, there were some very industrious Italians who read Riemann's paper back in the 19th century and figured out all sorts of things you can do to the Riemann tensor. Basically, you can distill it down. So you can contract, as they say, the Riemann tensor to make something called the Ricci tensor, after Professor Ricci. And the Ricci tensor only has 2 indices. And then you can actually contract that again to get something called the curvature scalar. So when Einstein is trying to think of what can he put on the left-hand side of his new equation for gravity, he has various ingredients to play with. He has the Riemann tensor, but also the Ricci tensor, and also the curvature scalar. Now you're instantly going to guess. I want to take the Ricci tensor, because it has 2 indices. I'm going to set it equal to the energy momentum tensor, which also has 2 indices. If you're guessing that, congratulations, you are just as smart as Albert Einstein, because he guessed that. It didn't work. It doesn't work because energy is not conserved in various other problematic things. But again, because he was Einstein, he worked harder, and he came up with this thing. R mu nu minus 1/2 r g mu nu equals 8 pi g t mu nu. That is the correct generalization of Newton's equation to the relativistic context. We now call this Einstein's equation. You saw it a few minutes ago, but now you perfectly understand it. But the point is, you see why, even if your understanding is only 99%, not 100%, you see that it's not just showing off or egregious, right? Like, these symbols have meaning. These mu's and nu's talk about directions in space-time. They will take on different values, 0, 1, 2, 3. R on the left and G on the left are different geometric quantities telling you about the curvature of space-time. T mu nu on the right is telling you about energy momentum. G is Newton's constant of gravity. 8 and pi you've met before. So if you get this far and you appreciate that now you have an equation, the next step, of course, just like for Newton's equation, is to solve the equation. What that means is, what you want to know is the metric on space-time. So the metric is what you need to actually calculate the force on a rocket ship or a planet or whatever, or a black hole, okay? The metric is implicit here because you use the metric to define the Riemann tensor and the Riemann tensor to define the Ricci tensor and the curvature scalar, but it's a little indirect. In fact, it's kind of like super duper indirect. So just to let you know, I've written out one component of the Riemann tensor in terms of the metric. Here it is. So in principle, you could say, all right, I'm going to be plucky. You assign your least favorite graduate student the job of trying very hard to solve this. And Einstein himself realized the level of complication, the number of mathematical operations you have to go through to go from metric to Riemann and back and forth and solve his equation. And he said this, no one's ever going to do this. I'm not going to do this, and I'm Einstein. So no one else is going to do this. Carl Schwarzschild went and did it. Schwarzschild is a fascinating story. He was an astronomer and mathematician by trade, but it was, remember, look at the dates on this. 1917. There was a war on, you might remember, right? World War I. And Schwarzschild, because he was good at math, was given the task of calculating ballistic trajectories for the Germans fighting the Russians on the Eastern Front. But they were, I don't know what the details were, but apparently there was shore leave or something. And it's not the Navy, so it's not shore leave, but he had some time off from fighting at the front, and he was allowed to go to Berlin, and he spent his time off listening to lectures by Einstein on relativity. It's a choice. You can't argue that. And Einstein gives his equations, and he says no one's going to solve them. Schwarzschild goes back to the front, and he sits down and solves them. So how can you possibly do this? Well, you make a lot of guesses. You make a lot of assumptions, right? You say, that doesn't sound very sciencey. I'm going to use the German word. I'm going to call it an Ansatz. An Ansatz is a guess. And in this case, what Schwarzschild said is, look, I don't care about the general arbitrary solution to anything. I care about the Earth moving around the sun. So I'm going to ignore, actually, the Earth and Jupiter and everything. I'm going to take the sun, put it in the middle of my coordinate system. I'm going to use spherical coordinates, just like we talked about. So rather than t, x, y, z, it's t, r, theta, phi, as you can see in the equation up here. And I'm going to assume all the off-diagonal elements are 0, and et cetera, et cetera. And I'm going to assume everything is static, nothing is vibrating. And then he actually whittled the problem down to something you could actually solve. And this expression here is the celebrated Schwarzschild metric. This is the exact metric for a perfectly spherical, empty space solution to Einstein's equation outside a star or planet or something like that. And Einstein himself saw it and was instantly impressed. That's memorable because Einstein was handed lots of papers and he was not usually instantly impressed. He usually had a reason to disbelieve them. For Schwarzschild's solution, he was very, very happy. Now, from here, now you're cooking with gas. Now you can calculate the motion of the Earth around the sun, or more importantly, the motion of Mercury. You can calculate gravitational lensing and gravitational redshift and a whole bunch of other predictions. One of the reasons why Einstein so quickly became a celebrity is because his equation led to predictions which were tested and successful at them. Arthur Eddington led an expedition to look for the gravitational lensing of light during a solar eclipse. It is believed that he was less than perfectly rigorous with the data, but he got the answer that he knew he wanted to get. And Einstein was very happy. But I don't want to talk about that now. We're running out of time, so let me just talk about one fact that you can glean from this equation. I want to let you know that it's not just some symbols here. You can get something out of them. So remember, we have interpretations or meaning for these different components of the metric tensor, right? GTT is the rate at which time flows for an observer compared to the time coordinate, etc. Then you look at this, and you look at GTT, it's the upper left-hand corner, right? 1 minus 2gm over r. R is the radial coordinate, g is Newton's constant, m is the mass of the thing. And you go, wait a minute.
Arrived at your destination.
When r equals 2gm, this whole quantity equals 0. It's 1 minus 1. So time isn't flowing? Something like that? What is going on at r equals 2gm? And then you look at the RR component, the next one down, diagonally, and it is, if the TT component was 0, this one is minus the reciprocal of 0, 1 over 0, which is infinity, and that's bad. So as soon as you write this down, you're like, Something weird seems to be happening at r equals 2 GM. So what did people do? Well, they said they calculated the value of r equals 2 GM. So you know the mass of the sun, you know the radius of the sun. At what radius are we talking about? And what you very quickly find is that the relevant value of r, which is now called the short shield radius, is much, much smaller than the actual radius of the sun. And this solution is only supposed to be valid outside the surface of the sun, not deep into the interior. So people said, and correctly, the fact that this metric seems to go haywire when r equals 2 GM is not physically relevant for things like the sun, the earth, etc. It only refers to places where the solution is not supposed to be valid anyway. Some more imaginative astronomers said, yes, but what if the thing collapses? You can see a 3-hour biopic about one of them if you go to see Oppenheimer. Oppenheimer and his student Harlan Snyder solved not for the static case, but they allowed a sphere of mass to collapse. And they showed that it collapsed and went right beyond the short shield radius. So this could be relevant physically. What is it? You all know what it is. It's a black hole. Here's a picture of a black hole. Not the black hole, you know what I mean. It's the picture of the light going nearby a black hole. This is from the Event Horizon Telescope. But here, just to make it vivid, remember, what is G00, GTT? It's how fast time flows compared to the time coordinate. I'm plotting it now. 1 minus 2 GM over R. So this is R in units of GM on the horizontal axis, and there's G00. And so you see that at R equals 2 GM, this number goes to 0. So at that place, the rate of passage of time experienced is 0. From the point of view of an outside observer, we call that place the event horizon. It took decades of clever mathematical work. It wasn't really until the 50s that people figured out how to just change coordinates, and there wasn't a barrier that you hit at the event horizon. You could just go right through it if you wanted to. These coordinates aren't very good there, but coordinates are just human inventions. They're nothing very deep. And furthermore, there was work by people like Chandrasekhar and others that showed that these collapses can actually happen in the real world. And finally, they started saying in the 50s and 60s, maybe these black holes actually exist. Nowadays, of course, we take pictures of them, give out Nobel Prizes like candy for people who are observing them in various ways. And the point of this is the last slide, which is that the reason why we care about these equations so much is because the equations are smarter than we are. Albert Einstein was pretty smart. He derived that equation that we show you here in the middle of the slide. But he never knew about black holes. He never fully understood gravitational waves. He was always somewhat uncomfortable with the idea of the Big Bang. The equations just sat back smugly and said, you'll figure it out eventually. And we're getting there. Same thing with Newton's equations, or with Maxwell's equations, or with Schrodinger's equation of quantum mechanics. We do some experiments locally here in our short, brief lifetime. We make some leaps of imagination to distill all of this complex physical behavior down to this little concrete poem. And then we blindly extend it to circumstances we haven't even imagined seeing yet. And a good equation is going to teach us something that will go, yep, the equation knew it all along. Thank you.
The following is a conversation with Roger Penrose, physicist, mathematician, and philosopher at University of Oxford. He has made fundamental contributions in many disciplines, from the mathematical physics of general relativity and cosmology to the limitations of a computational view of consciousness. In his book, The Emperor's New Mind, Roger writes that, quote, "Children are not afraid to pose basic questions that may embarrass us as adults to ask." In many ways, my goal with this podcast is to embrace the inner child that is not constrained by how one should behave, speak, and think in the adult world. Roger is one of the most important minds of our time, so it was truly a pleasure and an honor to talk with him. This conversation was recorded before the outbreak of the pandemic. For everyone feeling the medical, psychological, and financial burden of the crisis, I'm sending love your way. Stay strong. We're in this together. We'll be in this thing. This is the Artificial Intelligence Podcast. If you enjoy it, subscribe on YouTube, review it with 5 stars on Apple Podcasts, support it on Patreon, or simply connect with me on Twitter at Lex Friedman, spelled F-R-I-D-M-A-N. As usual, I'll do a few minutes of ads now, and never any ads in the middle that can break the flow of the conversation. I hope that works for you and doesn't hurt the listening experience. Quick summary of the ad. 2 sponsors, ExpressVPN and Cash App. Please consider supporting the podcast by getting ExpressVPN at expressvpn.com/LexPod and downloading Cash App and using code LEXPODCAST. This show is presented by Cash App, the #1 finance app in the App Store. When you get it, use code LEXPODCAST. Cash App lets you send money to friends, buy Bitcoin, and invest in the stock market with as little as $1. Since Cash App does fractional share trading, let me mention that the order execution algorithm that works behind the scenes to create the abstraction of the fractional orders is an algorithmic marvel. Big props to the Cash App engineers are solving a hard problem that in the end provides an easy interface that takes a step up to the next layer of abstraction over the stock market, making trading more accessible for new investors and diversification much easier. So again, if you get Cash App from the App Store or Google Play and use the code LEXPODCAST, you get $10. Cash App will also donate $10 to FIRST, an organization that is helping to advance robotics and STEM education for young people around the world. This show is sponsored by ExpressVPN. Get it at expressvpn.com/LexPod to get a discount to support this podcast. I've been using ExpressVPN for many years. I love it. It's easy to use. Press the big power on button and your privacy is protected. And if you like, you can make it look like your location is anywhere else in the world. I might be in Boston now, but I can make it look like I'm in New York, London, Paris, or anywhere else. This has a large number of obvious benefits. Certainly, it allows you to access international versions of streaming websites like the Japanese Netflix or the UK Hulu. ExpressVPN works on any device you can imagine. I use it on Linux, shout out to Ubuntu, Windows, Android, but it's available everywhere else too. Once again, get it at expressvpn.com/LexPod to get a discount and to support this podcast. And now, here's my conversation with Roger Penrose. You mentioned in conversation with Eric Weinstein on the Portal podcast that 2001 Space Odyssey is your favorite movie. Which aspect, if you could mention, of its representation of artificial intelligence, science, engineering connected with you?
There are all sorts of scenes there which are so amazing. And how science was so well done. I mean, people say, oh no, Interstellar is this amazing movie, which is the most scientific movie. But I thought it's another patch on 2001. I mean, 2001, they really went into all sorts of details about getting the free fall well done and everything. I thought it was extremely well done.
So just the details were mesmerizing. In terms
and also
of
things like the scene where at the beginning they have these sort of human ancestors, which are sort of sort of apes becoming
the
human.
monolith.
Yes, and well, it's the one where he throws the bone up into the air, and then it becomes this. I mean, that's an amazing sequence there.
What do you make of the monolith? Does it have any scientific or philosophical meaning to you? This kind of thing that sparks innovation?
Not really. That comes from Arthur C. Clarke. I was always a great fan of Arthur C. Clarke.
So it's just a nice plot device.
Yeah, that plot was excellent, yes.
So HAL 9000 decides to get rid of the astronauts because she believes that they will interfere with the mission.
That's right. Yeah, well, there you are. It's this view. I don't know whether I disagree with it, because in a certain sense it was telling you it's wrong. See, the machine seemed to think it was superior to the human, and so it was entitled to get rid of the human beings and run the show itself.
Well, do you think HAL did the right thing? Do you think HAL's flawed, evil, or if we think about systems like HAL, would we want HAL to do the same thing in the future? What was the flaw there?
Well, you're basically touching on questions, you see. Is one supposed to believe that HAL was actually conscious? I mean, it was played rather that way, as though HAL was a conscious being.
Because HAL showed some pain, some cognizant. HAL appeared to be cognizant of what it means to die.
Yes.
And therefore had an inkling of consciousness.
Yeah. I mean, I'm not sure that aspect of it was made completely clear, whether HAL was really just a very sophisticated computer, which really didn't actually have these feelings and somehow. But you're right, it didn't like the idea of being turned off.
How does it change things if HAL was or wasn't conscious?
Well, it might say that it would be wrong to turn it off if it was actually conscious. I mean, these questions arise if you think... I mean, AI, one of the ideas, it's sort of a mixture in a sense. You say, if it's trying to do everything a human can do, and if you take the view that consciousness is something which would come along when the computer is sufficiently complicated, sufficiently whatever criterion you use to characterize its consciousness in terms of some computational criterion.
So how does consciousness change our evaluation of the decision that HAL made?
Well, I guess I was trying to say that people are a bit confused about this. Because if they say these machines will become conscious, but just simply because it's a degree of computation, and when you get beyond that certain degree of computation, it will become conscious, then of course you have all these problems. I mean, you might say, well, one of the reasons you're doing AI is because you want to send a device out to some distant planet, and you don't want to send a human out there, because then you'd have to bring it back again, and that costs you far more than just sending it there and leaving it there. But if this device is actually a conscious entity, then you have to face up to the fact that that's immoral. And so the mere fact that you're making some AI device and thinking that removes your responsibility to it would be incorrect. And so this is some flaw in that kind of viewpoint. I'm not sure how, people who take it very seriously. I mean, I had this curious conversation with I'm going to forget names, I'm afraid, because this is what happens to me right long moment. Douglas Hofstadter.
Yeah.
And he had written this book,
God will let you off.
Which I liked. I thought it was a fantastic book. But I didn't agree with his conclusion from Gödel's theorem. I think he got it wrong, you see. Well, I'll just tell you my story, you see, because I'd never met him. And then I knew I was going to meet him. The occasion I realized he was coming in, he wanted to talk to me, and he said, that's fine. And I thought in my mind, well, I'm going to paint him into a corner, you see, because I'll use his arguments to convince him that certain numbers are conscious. Some integers, large enough integers, are actually conscious. And this was going to be my reductio ad absurdum. So I started having this argument, and he simply leapt into the corner. He didn't even need to be painted into it. He took the view that certain numbers were conscious. I thought that was a reductio ad absurdum, but he seemed to think it was a perfectly reasonable point of view.
Without the absurdum there.
Yes.
Interesting, but the thing you mentioned about HAL is the intuition that a lot of the people, at least in the artificial intelligence world, had and have, I think. They don't make it explicit, but that if you increase the power of computation naturally consciousness will emerge.
Yes, I think that's what they think. But basically that's because they can't think of anything else.
Well, that's right.
And so it's a reasonable thing. I mean, you think, what the brain do? Well, it does do a lot of computation. I think most of what you actually call computation is done by the cerebellum. I mean, this is one of the things that people don't much mention. I mean, I come to this subject from the outside, and certain things strike me, which you hardly ever hear mentioned. I mean, you hear mentioned about the left-right business. You move your right arm, that's the left side of the brain, and so on, and all that sort of stuff. And it's more than that. If you have these plots of different parts of the brain, there are two of these things called the homunculi, which you see these pictures of a distorted human figure and showing different parts of the brain controlling different parts of the body. And it's not simply things like, okay, the right hand is controlled and both sensory and motor. Left side, left hand on the right side. It's more than that. Vision is at the back, basically. Your feet at the top. And it's as though it's about the worst organization you can imagine.
Right, yeah.
So it can't just be a mistake in nature. There's something going on. And this is made more pronounced when you think of the cerebellum. The cerebellum has, when I was first thinking about these things, I was told that it had half as many neurons or something like that, comparable. And now they tell me it's got far more neurons than the cerebrum. The cerebrum is this sort of convoluted thing at the top people always talk about. Cerebellum is this thing just looks a bit like a ball of wool right at the back underneath. It's got more neurons. It's got more connections. Computationally, it's got much more going on than the cerebrum. But as far as we know, although it's slightly controversial, the cerebellum is entirely unconscious. So the actions, you have a pianist who plays an incredible piece of music and you think of, and he moves his little finger into this little key to get it hit at just the right moment. Does he or she consciously will that movement? No. Okay, the consciousness is coming in. It's probably to do with the feeling of the piece of music that's being performed and that sort of thing, which is going on. But the details of what's going on are controlled, I would think, almost entirely by the cerebellum. That's where you have this precision, the really detailed. Once you get, I mean, you think of a tennis player or something. Does that tennis player think exactly how which muscle should be moved in what direction and so on? No, of course not. But he or she will maybe think, well, if the ball is angled in such a way in that corner, that will be tricky for the opponent. And the details of that are all done largely with the cerebellum. Because that's where all the precise motions, but it's unconscious.
So why is it interesting to you that so much computation is done in the cerebellum and yet it is unconscious?
Because it doesn't, it's the view that somehow it's computation which is producing the consciousness. And it's here you have an incredible amount of computation going on, and as far as we know, it's completely unconscious. So what's the difference? And I think it's an important thing. What's the difference? Why is the cerebrum, well, all this very peculiar stuff that very hard to see on a computational perspective, like having everything have to cross over onto the other side and do something which looks completely inefficient. And you've got funny things like the frontal lobe and the whatever we call the lobes, and the place where they come together. You have the different parts, the control, you see one to do with motor and the other to do with sensory. And they're sort of opposite each other rather than being connected by it's not as though you've got electrical circuits. There's something else going on there. So it's just the idea that it's like a complicated computer just seems to me to be completely missing the point. There must be a lot of computation going on, but the cerebellum seems to be much better at doing that than the cerebrum is.
So for sure, I think what explains it is like half hope and half we don't know what's going on, and therefore, from the computer science perspective, you hope that a Turing machine can achieve general intelligence.
Well, you have this wonderful thing about Turing and Gödel and Church and Carreer and various people, particularly Turing, and I guess Post was the other one. These people who developed the idea of what a computation is. And there were different ideas of what a computation developed differently. I mean, Church's way of doing it was very different from Turing's. But then they were shown to be equivalent. And so the view emerged that what we mean by a computation is a very clear concept. And one of the wonderful things that Turing did was to show that you could have what we call a universal Turing machine. You just have to have a certain finite device. Okay, it has to have an unlimited storage space, which is accessible to it, but the actual computation, if you like, is performed by this one universal device. And so the view comes away, well, you have this universal Turing machine, and maybe the brain is something like that, a universal Turing machine, and it's got maybe not unlimited storage, but a huge storage accessible to it. And this model is one which is what's used in ordinary computation. It's a very powerful model. And the universalness of computation is very useful. You can have some problem and you may not see immediately how to put it onto a computer, but if it is something of that nature, then there are all sorts of sub-programs and subroutines. I mean, I learned a little bit of computing when I was a student, but not very much. But it was enough to get the general ideas.
And there's something really pleasant about a formal system like that, where you can start discussing about what's provable, what's not, these kinds of things.
And you've got a notion which is an absolute notion. It's not a notion of computability. You address when things are, what mathematical problems are computably solvable and what aren't. And it's a very beautiful area of mathematics, and it's a very powerful area of mathematics, and it underlies the whole sort of the principles of computing machines that we have today.
Could you say what is Gödel's incompleteness theorem, and how does it, maybe also say, is it heartbreaking to you, and how does it interfere with this notion of computation and consciousness?
Sure. Well, the ideas, basically, ideas which I formulated in my first year as a graduate student in Cambridge. I did my undergraduate work in mathematics in London, and I had a colleague, Ian Percival, who used to discuss things like computational and logical systems quite a lot. I'd heard about Gödel's theorem. I was a bit worried by the idea that it seemed to say there were things in mathematics that you could never prove. And so when I went to Cambridge as a graduate student, I went to various courses. You see, I was doing pure mathematics. I was doing algebraic geometry of a sort, a little bit different from my supervisor and people, but it was algebraic geometry. And I was interested, I got particularly interested in 3 lecture courses that were nothing to do with what I was supposed to be doing. One was a course by Hermann Bondi on Einstein's general theory of relativity, which was a beautiful course. He was an amazing lecturer, brought these things alive, absolutely. Another was a course on quantum mechanics, given by the great physicist Paul Dirac. Very beautiful course in a completely different way. He was very kind of organized and never got excited about anything, seemingly. But it was extremely well put together, and I found that amazing too. Third course that was nothing to do with what I should be doing was a course on mathematical logic. I got, as I say, my discussions with Ian Percival.
Was the incompleteness theorem already deeply within mathematical logic space? Were you introduced
I was introduced to it in detail by the course by Steve. And it was 2 things he described which were very fundamental in my understanding. One was Turing machines, and the whole idea of computability and all that. So that was all very much part of the course. The other one was the Gödel theorem. And it wasn't what I was afraid it was, to tell you there were things in mathematics you couldn't prove. It was basically And he phrased it in a way which often people didn't. And if you read Douglas Hofstadter's book, he doesn't, you see. But Steen made it very clear. And also in a sort of public lecture that he gave to a mathematical, I think maybe the Adams Society, one of the mathematical undergraduate societies, and he made this point again very clearly. But if you've got a formal system of proof, so suppose what you mean by proof is something which you could check with a computer. So to say whether you got it right or not, you've got a lot of steps. Have you carried this computational procedure, well, following the proof, steps of the proof correctly? That can be checked by an algorithm, by a computer. So that's the key thing. Now what you have to, now you see, is this any good? If you've got an algorithmic system which claims to say, yes, this is right, this you've proved it correctly, this is true. If you've proved it, you made a mistake, it doesn't say it's true or false, but if you've done it right, then the conclusion you've come to is correct. Now you say, why do you believe it's correct? Because you've looked at the rules and you said, well, okay, that one's all right, yeah, that one's all right, what about it? Oh, I'm not sure. Oh, yeah, I see why it's all right. Okay, you go through all the rules, you say, yes, following those rules, if it says, yes, it's true, it is true. You've got to make sure that these rules are ones that you trust. If you follow the rules and it says it's a proof, is the result actually true? And that your belief that it's true depends upon looking at the rules and understanding them. Now what Gödel shows is that if you have such a system, then you can construct a statement of the very kind that it's supposed to look at, a mathematical statement, and you can see by the way it's constructed and what it means that it's true, but not provable by the rules that you've been given. And it depends on your trust in the rules. Do you believe that the rules only give you truths? If you believe the rules only give you truths, then you believe this other statement is also true. I found this absolutely mind-blowing. When I saw this, it blew my mind. I thought, my God, you can see that this statement is true. It's as good as any proof, because it only depends on your belief in the reliability of the proof procedure, that's all it is, and understanding that the coding is done correctly, and it enables you to transcend that system. So whatever system you have, as long as you can understand what it's doing and why you believe it only gives you truths, then you can see beyond that system. Now, how do you see beyond it? What is it that enables you to transcend that system? Well, it's your understanding of what the system is actually saying and what the statement that you've constructed is actually saying. So it's this quality of understanding, whatever it is, which is not governed by rules. It's not a computational procedure.
So this idea of understanding is not going to be within the rules of within the formal system.
Yes, you're only using those rules anyway, because you have understood them to be rules which only give you truth. There'd be no point in it otherwise. I mean, people say, well, okay, this is one set of rules is as good as any other. Well, it's not true. So you have to understand what the rules mean. And why does that understanding mean give you something beyond the rules themselves? And that's what it was. That's what blew my mind. But somehow, understanding why the rules give you truths enables you to transcend the rules.
So that's where, I mean, even at that time, that's already where the thought entered your mind that the idea of understanding, or we can start calling it things like intelligence or even consciousness, is outside the rules.
Yes. See, so I've always concentrated on understanding. You know, people come and point out things. Well, we know, what about creativity? That's something a machine can't do. Is create. Well, I don't know. What is creativity? And I don't know. And, you know, somebody can put some funny things on a piece of paper and say that's creative, and you could make a machine do that. Is it really creative? I don't know. You see, I worry about that one. I sort of agree with it in a sense, but it's so hard to do anything with that statement. But understanding, yes, you can. You can go see that understanding whatever it is, and it's very hard to put your finger on it. That's absolutely true.
Can you try to define or maybe dance around a definition of understanding?
To some degree, but I often wondered about this. But there is something there which is very slippery. is something like standing back. And it's got to be something, you see, it's also got to be something which was of value to our remote ancestors.
Right.
Because sometimes there's a cartoon which I drew sometimes showing you how all these, in the foreground you see this mathematician just doing some mathematical theorem. There's a little bit of a joke in that theorem, but let's not go into that. He's trying to prove some theorem, and he's about to be eaten by a saber-toothed tiger who's hiding in the undergrowth, you see. And in the distance you see his cousins building, growing crops, building shelters, domesticating animals. And in the slight foreground you see they built a mammoth trap, and this poor old mammoth is falling into a pit, you see, and all these people around him are about to grab him, you see. And well, you see, those are the ones who, the quality of understanding which goes with it's not just the mathematician doing his mathematics. This understanding quality is something else, which has been of tremendous advantage to us, not just to us. See, I don't think consciousness is limited to humans.
Yeah, that's the interesting question. At which point, if it is indeed connected to the evolutionary process, at which point did we pick up this?
Very hard question. It's certainly, I don't think it's primates. You see these pictures of African hunting dogs and how they can plan amongst themselves how to catch the antelopes. Some of these David Attenborough films, I think it's probably one of them. And you can see they're hunting dogs. And they divide themselves into two groups. And they go in two different groups. One of them goes and they sort of hide next to the river. And the other group goes around and they start yelping at these. They don't bark, I guess, whatever noise hunting dogs do. The antelopes, and they sort of round them up and they chase them in the direction of the river. And they're the other ones just waiting, just to get, because when they get to the river it slows them down. And so they pounce them. So they've obviously planned this all out somehow. I have no idea how. And there is some element of conscious planning as far as I can see. I don't think it's just some kind of... so much of AI these days is done on what they call bottom-up systems, is it? Yeah. Right. Where you have neural networks and you give them a zillion different things to look at, and then they sort of can choose one thing over another just because it's seen so many examples and picks up on little signals which one may not even be conscious of.
And that doesn't feel like understanding.
There's no understanding in that whatsoever. So,
well, you're being a little bit human-centric, so...
Well, I think I would expect... I'm not with the dogs, am I?
No, you're not. Sorry, not human-centric, but I misspoke. Biology-centric. Is it possible that consciousness would just look slightly different?
Well, I'm not saying it's biological, because we don't know.
Right.
I think other examples with the elephants is a wonderful example, too. Where I think this was an Attenborough one, where the elephants have to go from the troop of them have to go long distances. And the leader of a troop is a female, they all are apparently. And this...
Great to see everyone. It's great to see so many happy faces. IT is a first. It's the first time For those of you who don't know who we are, the London Institute for Mathematical Sciences is Britain's only independent research center in physics. Scientists have been crying out for a place where they can dedicate themselves full-time to what they do best, making fundamental discoveries. They don't get to do that at universities. At the London Institute, we speed up discovery by letting scientists do science full-time. Think of us as a place for full-time Penroses working at top speed.
So in February this year, we're so honored to be invited here to move into the Royal Institution. And in fact, the London Institute occupies the very set of rooms that Michael Faraday used to live in. It's right there upstairs. Okay, so we're not the Royal Institution, but we're at the Royal Institution.
The second way this is the first time that Roger Penrose has sat down in casual conversation with mathematicians to talk about his science, himself, and the way his mind works.
Right. So, for those of you who don't know who Sir Roger Penrose is, you're clearly at the wrong event. Martin has kindly pointed out where the exits are, so just please leave quietly. I'm very privileged to have known Roger for a number of years as a colleague. And in 2019, I was so delighted and honored that Sir Roger wrote a chapter as a contribution to my latest book, Topology and Physics. And when Roger turned in his exquisite chapter on singularity theorems, which we're going to talk about shortly, it confirmed a suspicion I had a very long time. Surely this man is going to get the Nobel Prize.
Sir Roger is a mathematical physicist with the eye of an artist and the soul of a philosopher. He's also a master wordsmith capable of turning very complex ideas and making them look simple. He's also been an inspiration for a generation of physicists and mathematicians alike.
So nobody's left, so I guess everybody knows that Roger Penrose did indeed receive the Nobel Prize in 2020 for physics. But you may not know that he also is the holder of OM, which stands for Order of Merit. So I'm going to do a little bit of calculation for here on the board. Chalk on blackboard. This is what we do at the London Institute. It's like kids in a candy store. This is what this is all about. So here's a calculation for you, okay? So the Nobel Prize was founded by Alfred Nobel in 1901. The OM, Order of Merit, was founded by King Edward VII around about the same time. To date, there has been 962 recipients of the Nobel Prize, of which there's approximately 120 alive right now. The OM has gotten 196 in its history, and by definition, can never exceed. Therefore, by both measures, you can clearly see that the OM is about 5 times harder to get than the Nobel Prize. And Sir Roger has both.
So nice to be back.
Yes, indeed.
Yes.
So maybe, if you don't mind, we can just kick right in to the topic about the black hole which you want the prize. So could you please really give for layers some of the background? Let's go start at the very beginning of our journey. Some of the background. What were the thoughts about black holes and general relativity when you got interested in the subject?
Well, there was a paper published in 1930 by Oppenheimer, Oppenheimer was a student of Snyder, and they wrote this paper which was about a dust cloud, so it was a spherical ball of dust, which had reached a level where it could collapse inwards through its own gravitational field, and it would go inwards and inwards and inwards. And the picture was what we now think of as a black hole. This was in 1939, just before the war. And since the body was... Well, first of all, what's dust? Dust meant a material which has no pressure. There was nothing to stop it from pressure. Secondly, it falls radially inwards. It's exactly spherically symmetrical. So the fact that it meets in the middle, and when it gets into the middle, the density becomes infinite, and so when the density is infinite, you get to what's called a singularity, where according to Einstein's theory of general relativity, the space-time curvature becomes infinite, and so you have nonsense in the middle. And so this picture was around at that time. I don't know that people took it very seriously. It was an idealization. You had to get this big cloudy dust, which was kind of thought to be firing towards itself. And it had to be no pressure. It had to be exactly spherically symmetrical, aimed towards the central point. So the fact you got this infinite density and therefore infinite curvature in the middle was not a surprise. This paper was lying around for quite a while. I did know about it. I was in Princeton I went to Princeton in 1959-60, and yes, 1959-60. And John Wheeler, went to work with him, and he was one of the people who was really interested in this issue of what's called gravitational collapse. But it was taken as a very theoretical thing. But the excitement really came, I think it was in the early 1960s, slightly earlier than that, when these objects called quasars were discovered. I don't know whether you can say objects were discovered. The signals from them were discovered. These were radio signals, and they were of such an intensity, and also they were redshifted. That meant that they either came from something very, very dense, or more likely were taking part in the expansion of the universe and were extremely distant. So these objects were extremely distant and extremely energetic. They were emitting more energy at that sort of distance than from 1,000 galaxies. A large, enormous amount. But also they couldn't be extraordinarily large. I think that sounds because the radiation was varying to a degree which indicated that it couldn't be larger than the solar system, at least, probably a lot smaller than that, in order that if it could change in intensity coherent way, it couldn't one part communicate with another as it took so long for a light signal to get from one side to the other. So it had to be relatively small, considerably smaller than the galaxy. And so people began to wonder whether these were objects of the sort of size and concentration that you have in this picture. The trouble is that picture, just everything falls into the middle, nothing comes out, you wouldn't get any signals out. So it couldn't be just that. Might be something more complicated, swishing around in some way. And that was the question that was raised. I know from February there was some toying with the idea that there wasn't some body of this kind of scale that we would think of. The terminology had arisen, and they couldn't be spherically symmetrical, otherwise you wouldn't get those signals. What's more, at that time, when I was at that time, 1964, I guess, there was a paper written by two Russians, and they had an argument to show that in the general case, according to Einstein's general theory, in the general case, you would not get singularities. So if the density or curvature started to get too big, it would sort of swirl out again. And you wouldn't get singularities. And that was the paper they'd written. And John Wheeler was very interested in this question of gravitation. And I was but he said earlier when I was working and I began wondering, well, if it was complicated and irregular, do you believe what I should say? That it's better go singular. I had a look at the paper. I was not completely convinced by the methods that were used. There was actually a serious mistake, which they later corrected. But at the time, it seemed to be the case that you couldn't do singularities. But as I say, I was not totally convinced by that. So I began to think about this. I began to imagine what it would be like inside one of this swirling and collapsing stuff. And I tried to think of some way of characterizing it having reached a particular time. I didn't have a good characterization at the time, but that I had written a paper. This was a paper on something different, which I'd sent to the Royal Society. It was about gravitational fields and electromagnetic fields and what they behaved like when you went very far away. And as part of the argument, I needed to have a result. I'm not going to go into it, but I thought I might as well just assume this was a assume. But nevertheless, I thought perhaps we could prove it. And in the appendix, I put an argument there which used the type of argument which turned out to be useful in this I wasn't
arrived at your destination.
I was just thinking, like, if you have some region in space-time and you look at the future of that region. So when I say by the future of that region, I mean if you have all particles starting at that region and they're going, if you like, as fast as they can away from it, what kind of a region do they trace out and what's the boundary of that region? So that's the sort of thing I had to think about. But I had no way of seeing how to apply this to the... I happened to be, at the time, this was in 1964, and I happened to be working, I lived in Stanmore, so I came up to, I walked through the Woodstock to the tube station, I came up to and I was walking towards where I worked, which was at Berkeley College, and I was accompanied by Ivor Robinson, who was a good friend of mine, who was an Englishman who happened to be working in Dallas, Texas. He had this wonderful way with words. I didn't know anybody who played with words in the way he did. It was just fantastic. And the Americans all loved him. It was just so different.
You've arrived at your destination.
He was a very clever chap, and he had worked on solutions of the Einstein equations using very ingenious methods. So he was talking to me and waving his hands around in his way about something which I'd completely forgotten, I'm afraid. Probably something about his solutions in general relativity. Anyway, it was very interesting. And we came to this side road. I think it was Mallet Street. Something I did. And we came to the side road, and we had to check there was no traffic there. And so the conversation stopped. We got to the other side. And stopped. And then he went off. And I remember having a strange feeling of elation.
You've arrived at your destination.
Was it the walk through the woods? I don't think so. Was it catching the train? No, I don't think so. I just all the things. And finally I got down to this place where the conversation stopped and I crossed the road. Gosh, I had an idea then. I've almost lost it altogether. But I had this idea, which was what I called a trapped surface. And this was basically a surface. You see, you had to have a criterion which didn't depend on the symmetry. Because, sure, this is just symmetry. It's a real situation on view. But the thought I had was this thing I called a trapped surface. And it's this kind of surface, it's a spherical surface. That means it has the topology of a sphere. It can be wiggly. It doesn't have to be exactly a sphere.
In fact, I think I have this. This is your paper.
Yes, that's the picture from, I think I can see it.
You can see it from there.
Yes. Well, actually, I can't see that. My eyes are not good enough. But I can see this one.
So the audience can see.
Yes. No, I know what it is.
Right,
Yes.
right.
Yes, that little black ring in the middle. You have to imagine, of course, that you've got one more dimension. This is only a 2 plus 1. That is 2 space and 1 time dimension.
Right.
The time is going up. Space is going round. But you've got to have one more dimension. And that thing that looks like a ring in the middle is really a sphere. When I say it's a sphere, well, it is a sphere. Right. But you imagine a flash of light coming instantaneously over that sphere. And because it's, well, what's called inside the horizon, there's that cylinder that you can see going up. That's where I could talk more about this details of this picture, but let me not because it'll take too long. But a flash of light on that thing that looks like a ring would be focused inwards. So the flash would, not just the inward, you see the flash would, there'd be an inward flash going inwards, and there'd be an outward flash, but the outward flash is going in too. That is to say, it's focusing inwards. So the light rays are converging, they're coming towards they're going inwards. And I knew once you had that situation that the future of that, what I call the trapped surface, and the boundary of that future would have certain properties that even if it was wiggly, it's not the exact picture, you imagine it wiggly, but don't wiggle it so much that the convergence becomes.
See the problem. In moments like this, access
so peaky.
Take advantage of their massive 50% discount on their top-tier Vantage plan and get access to every feature we've shown and more only a limited time. Use our link at ground.news/startup or scan the QR code to subscribe. As we continue exploring Kip Thorne's groundbreaking series, remember, Ground News can bring that same level of critical thinking to how you stay informed. Now, back to the show.
Well, I got another one. Okay, you're 1 for 1. All right. When they're on the black hole planet, okay, and then they see this wave coming.
Okay, it's Miller's planet.
Miller's planet.
That's
Sorry.
the water planet.
The planet orbiting Gargantua.
Mm-hmm.
Gargantua. Yeah. Okay. The strength of tidal forces are highly sensitive to the distance you are to that which is causing the tide. Highly sensitive. Okay? But every illustration I've drawn or taught about tides, they're not so peaky. They're much broader in their representation on a planet. And so there they are, wading in water, but then they see this single wave come. And if it is a single wave, as we've seen with tsunamis, it actually takes water away from what's ahead of it. Because it can't just be water out of nowhere. It's drawing water from its vicinity. So my 2 issues was, if it's tidal, would it be that peaky? And if it's any kind of wave, how could it still leave the water laying around its vicinity and then just be that big as it came by?
So there is a type of wave called a solitary wave on water that was...
Oh, you can tell me you brought wave people together and had that lunch. Is that what you're going to tell me?
No, this particular kind of wave was discovered in the 1700s by, I've forgotten who, a physicist in England who saw a boat that was being pulled by horses, and it was just starting up. And it created this wave that traveled down a channel, a canal, and it was peaked like the wave in Interstellar. Though the wave in Interstellar, I have to admit, it was exaggerated. There was
I don't mind exaggeration.
There was some exaggeration in the peak, but it traveled down the channel. It never broke. Most waves in the ocean, they break.
Okay, just so we can get the picture, because we're talking about centuries ago. When you say a channel, that would be a channel or a canal.
A canal.
And then there's a towpath on the side.
A towpath.
And then people, and more likely beasts of burden, would drag things through the canal. Because canals themselves don't typically have current.
Drag a barge down the canal.
A barge, exactly.
Yep. And so this barge was dragged down the canal, and it was just starting up, and it created this wave that
on the startup.
On the startup, and it just headed out and just took off and went down the channel. And this guy got on his horse and he followed down the channel. And it went down the channel. You gotta love
curious physicists. Nothing gets by.
And it went down the channel for I don't know, a mile or two, without changing its shape, without
breaking.
And so the theory of these waves is that
you and others decided to look differently for them.
Yeah. Well, so Ray Weiss.
Texas.
What?
All Texas.
All Texas, I know.
Might care to look at that, Peter.
What is it?
The essence of a man like me lies just in what he thinks and how he thinks, not in what he does or suffers.
The time had come for the rank amateur to try to grasp the way Einstein thought. Yes, said Nigel Calder, the writer, my journey was really necessary.
There's the observatory now.
What, there's two little white, whatever they are?
That's right.
There's a third one I can see now.
Yes, they're the domes. They keep a lookout for aircraft so as not to zap us with their laser beam.
You serious?
Quite serious.
They wanted me to speak Einstein's words and make the odd space flight, but mostly just to attend to the theory of relativity. I was promised a tale of how our perceptions of space and time and color are distorted according to where we are and how we're traveling. Amid such relativity, Einstein found reliable laws governing atoms, planets, stars, and all creation. Ah yes, an escort, perhaps to make quite sure I didn't funk the cerebral adventure they had in store for me.
Very nice flying.
Thank you, Fred. Thank you very much indeed. On my arrival, I knew only that Albert Einstein was a gentle genius whose reasoning anticipated our world of nuclear energy and space flight, the Big Bang, the black hole, things I'd only heard about. My tutors were to be leading experts assembled in this remote corner of Texas for my benefit and of yours. Our guides through Einstein's universe.
Dennis Sharma here is a theorist concerned with the overall nature of the universe. Roger Penrose, he pioneered the modern theory of black holes. You've heard of them.
Yes, I have, without understanding what they are.
Well, John Wheeler here said they had to exist and named them black holes, as a matter of fact. He's very much a grand old man of theoretical physics.
I see. There's some more... Oh, yes.
And Wallace Sargent here thinks he's discovered a huge black hole.
Well, he looks as if he's photographed just at the moment of discovery, doesn't he?
Very pleased with himself.
Yeah, with everything.
Erwin Shapiro, you'll hear how he's been getting radar echoes from the planets.
Yes.
And Sidney Drells, a theorist from the high-speed world of subatomic particles.
Gracious.
And Ken Brescher here, he's checked some of Einstein's basic assumptions with very precise astronomical tests.
A formidable range of expertise, but they looked friendly enough. I then became aware that there might be more to those motorcycles than met the eye. As we journeyed into the mountains, Calder told me that the theory of relativity burst upon the world more than 70 years ago, when special relativity proclaimed the curious effects of high-speed motion. General relativity, he said, followed later as Einstein's theory of gravity. But we were to take them in the reverse order and approach the bewildering distortions of time by way of a gravitational black hole. I'm just nosing in towards the black hole now. For our celebration of Einstein's relativity and the famous formula that powers the universe, the venue was the McDonald Observatory of the University of Texas, and the observatory's main telescope was our window on Einstein's universe. With a light-gathering mirror 107 inches wide, it's not the largest in the world, but a very impressive instrument all the same.
Oh, that's charming.
Isn't it, though?
Yes.
Quite a telescope.
Already I found a posse of relativists at my shoulder. And affording us the use of the telescope to embellish our little seminar was the director of the observatory, Harlan Smith.
The proper levity, but you see the gigantic counterweight here.
That's merely a counterweight?
Yes, many people ask what that's for, but it's just dead weight.
The air was decidedly thin on the mountaintop. They bring you up here, getting you in some sense closer to the stars, I suppose, and then present you with stairways at every turn.
More steps?
More steps. Just. You're standing very close to one of the portholes, which the light can emerge. We can put an instrument on there to analyze the light. It becomes a main collecting mirror. But it's also interesting to see the control console down there. It's really remarkably small for all the functions.
You mean that's the dashboard for this?
That's all it takes.
Well, this is McDonald, and this is Kit Peak. This one...
They did everything to help a greenhorn understand modern astronomy in its Einsteinian modes.
NASA tracking station in Madrid, the Bond telescope, yeah.
So basic are Einstein's ideas to modern knowledge that confirming them is now a global industry. When I prowled through the observatory, it seemed like a set for some drama in space. In a sense, it was. About science, Einstein and I had only this in common. We both hated the way it was taught to us at school. He transcended that, I drowned in it. John Wheeler began my rather belated rescue.
Thanks to your not being a scientist, we're all going to have to give this account the simplicity that Einstein would have loved. Where do you think we should start the account, John? With gravity? Nothing could be better. Everyone has to deal with it every day.
Gravity.
Well, let's see what the astronauts made of gravity on the moon.
I'm very proud to have the opportunity here to play postman. What could be a better place to cancel a stamp than right here at Hadley Rill?
I remember this from the time.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
I have here a hammer and a bird's feather.
How about that? If you were Galileo, how would you, in the light of that, try to persuade people that everything falls the same rate?
Difficult.
Difficult. Air resistance is a whole problem, isn't it? So such a wonderful thing that air resistance for objects like this doesn't count so much.
Fantastic.
What a feat for Galileo to realize that everything falls at the same rate. But for Einstein, it was a still greater act of imagination to realize that the reason those things all move the same, they get their moving orders from the same piece of space. It's not the distant Earth, it's the space right where they are.
Yeah, there came to me the happiest thought of my life. Consider someone in free fall, for example, from the roof of a house. There exists for him, during his fall, no gravitational field.
And Einstein really tells us that gravity
You got a pretty good idea what chemistry is, right? It's atoms and molecules doing stuff and making cars and food and life and everything. And of course, it's the study of those things. But like, how did we get here? There's certainly no everyday evidence for much of what we have discovered through the science of chemistry. Discoveries that were not derived or made up, but just laws of the universe that exist simply because the universe is the way the universe is. So in today's episode of Crash Course Chemistry, we're going to be taking a bit of a historical perspective on the creation of the science of chemistry. A science that didn't really even exist until a super smart, super wealthy French guy put the puzzle pieces together into a coherent theory for quite literally how everything works. And if you've ever found yourself sitting at your desk reading the same line in your chemistry book the 22nd time, and you think to yourself, the guy who invented chemistry should be put to death. Well, you should feel bad, because he was. Antoine Lavoisier was pretty fantastic. He was a geologist, a botanist, a biologist, and a physicist. He helped define the metric system, created an international language of chemistry, named hydrogen and oxygen, predicted the existence of silicon, outlined what elements were, figured out how animals extracted energy from food, determined that an element could take different forms upon discovering that both ash and diamond contained pure carbon, published the very first chemistry textbook ever, and there's a reason why the law of conservation of mass used to be called Lavoisier's law. Born into a wealthy family, Lavoisier inherited a massive amount of money when his mom died when he was 5 years old, And though he did get licensed to practice law as his father expected him to follow in his lawyerly footsteps, young Antoine chose science instead. When the opportunity arose to marry a wealthy girl whose father's massive income came from collecting taxes for the French government, he did it, even though she was 13? A questionable decision, though not uncommon at the time. It turned out that the family connections would be his undoing, though, not the age of the bride and her marriage. Marie-Anne, as she grew older, would become a colleague as well as a wife, assisting Antoine in his experiments and his analysis of the work of others. Indeed, it was Marie-Anne who translated Essay on Phlogiston for Antoine, which he ripped to pieces, changing everything forever. Until Antoine Lavoisier started inspecting everybody's work, the prevailing theory of chemical change was that some substances contained an elusive element called phlogiston. By burning these phlogiston-containing elements, they would lose their phlogiston and become new things. Lavoisier took those theories and their research, combined it with research being done elsewhere, and added in his own genius experiments, and then tore the chemical world to pieces with a little thing called combustion. He determined that hydrogen wasn't inflammable air, it was an element. Indeed, he named it hydrogen because it was generated from water, or hydrogenerated. And he determined that oxygen was a vital ingredient for combustion, and also what would later be known as oxidation, something that we'll discuss quite a lot in this course. By hooking people up to his bizarre contraptions, he determined that burning wood consumed the same amount of oxygen, and produced the same amount of carbon dioxide as people consuming food and breathing, thus determining that people, and all animals, are powered by some form of internal combustion. Now, experimenters of the day, I hesitate to call them chemists, notice that when you burn something, its mass decreased. Like, here's a fuse, and I put it on a scale, and I burn it, and its mass decreases. But Lavoisier determined that if all the particles in gas are collected, like if I burn the fuse inside a closed bottle, the mass stays the same. Stuff remained stuff. You can't lose any. You couldn't make more. This realization, though it seems obvious to us now, and its acceptance by the general scientific community, as far as I'm concerned, was the precise moment at which alchemy ended and chemistry began. Lavoisier's chief contributions and ultimately his discovery of the law of conservation of mass relied on careful measurement and careful thinking. And as you'll see, both of those things are key to success in chemistry to this day. Lavoisier the man was a bit of a dichotomy, having worked as a tax collector and helping to create a literal wall around Paris to assist in the collection of taxes, but also a supporter of the French Revolution as it began. But the enemies he had made with his wall, and by denying certain powerful politicians entry into the French Academy of Sciences, eventually caught up with him as the revolution's lunacy increased. He was beheaded on May 8th, 1794. Lavoisier was pardoned a year and a half after his execution, so that's good. Marie-Anne was delivered all of his confiscated belongings, and a note of apology, like, sorry we killed your husband, here's all the stuff back. The mathematician Joseph Lagrange said at the event, it took them only an instant to cut off that head, but France may not produce another like it in a century. It's worth noting, though this isn't really science talk, that Lavoisier couldn't have done any of his magnificently careful measurements had it not been for his enormous wealth. He commissioned the creation of hundreds of pieces of equipment, large and small. Only the system of economic inequality that the French were revolting against made it possible for Lavoisier to do his work. I'll leave you to think on the implications of that on your own. Lavoisier's work was, for a full century, the basis of all chemistry. Proving that you don't have to be rich to get a law at least temporarily named after you, French pharmacist Joseph Proust built on Lavoisier's ideas of extremely careful measurement, showing that a chemical compound always contains the same proportions of elements. For a while we called this Proust's law, but to make it easier to remember for the world, we just call it the law of definite proportions now. And then an English school teacher, John Dalton, followed Proust by examining what at first appeared to be a problem with Proust's work. Carbon and oxygen, when reacted together, would form two different proportions, not just one. Of course, what was happening is obvious to us. Carbon and oxygen were reacting to form two different compounds, carbon dioxide and carbon monoxide. As Dalton's work continued, he found something truly mind-bendingly fascinating. If you limited the amount of carbon reacting to exactly 1 gram, the mass of oxygen consumed to produce one compound was 1.33 grams, while the mass consumed to produce the other compound was 2.66, exactly double what was required for the other compound. This shook out for other reactions too. When reacting nitrogen and oxygen and limiting to exactly 1 gram of nitrogen, 3 compounds formed. One compound consumed 1.750 grams of oxygen, another consumed 0.8750 grams, and another consumed 0.4374 grams all of those numbers are relatable by small whole number ratios. Oxygen wasn't reacting with some ephemeral cloud of the idea of nitrogen. It was reacting with individual discrete bits of nitrogen that couldn't be divided. It could react in a number of ways, but it was always the same oxygen and the same nitrogen with the same properties. And so while in our first episode we showed you how Einstein actually proved that atoms exist with super fancy math, Dalton had used multiplication to become the first person to actually have real data supporting the idea of atoms. Dalton still, though, had it kinda wrong. He thought that the products of his reactions were elements as well. Basically, he believed that atoms and molecules were the same thing. We often simplify this and don't note Dalton's confusion on this particular point, but that leaves a couple of other fantastic chemists out of the story. For example, Joseph-Louis Gay-Lussac, who in 1804 became the highest scientist ever in history by taking a hot air balloon to the dangerous height of 7,000 meters to take air samples. But in addition to being maybe a little bit crazy, Gay-Lussac published a paper showing that a volume of oxygen gas is 2 times smaller than the volume of water vapor it creates, indicating that somehow oxygen was splitting into 2 pieces. Dalton would not accept this because it meant that oxygen was not 1 but 2 atoms, and apparently that just messed with his whole conception of the universe, and he never did accept it, even unto his death. It took an Italian house elf, genius, Lorenzo Romano Amadeo Carlo Avogadro di Quaregna e di Ceretto. I think the first time. We'll just call him Amadeo Avogadro, but he was a count, so he had to have a super fancy name, and I'm me, so I had to try to say it. Much like Lavoisier, Avogadro's political alliances would get him into trouble. After Napoleon's downfall in 1815, Avogadro was active in the Italian anti-monarchy revolution, possibly even sponsoring some revolutionaries with his personal fortune. For this, he lost his chair at the University of Turin, but thankfully he did not lose his head. Avogadro proposed, correctly, that any gas in a container of the same size with the same temperature and pressure would have roughly the same number of molecules in it, no matter what the gas was. So any difference in mass between 2 flasks of the same size full of 2 different gases would be because of a difference in the actual physical mass of the molecules. And thus, Avogadro basically figured out how to weigh atoms and molecules, as long as they were gaseous. To support his hypothesis, which was certainly good enough to support, he suggested that in forming water, oxygen gas would actually split into 2 oxygen atoms, what he called elementary molecules that could not be broken down any further. For some 50 years, Avogadro's idea of fundamental molecules were ignored, maybe because of incorrect ideas about how atoms stuck together, maybe because Italy was a bit of a backwater of science and Avogadro wasn't considered an important thinker at the time. But the scientific community, as it usually does, came back around to Avogadro's ideas eventually, not only naming his proposal that equal volumes at the same temperature and pressure contain the same number of molecules, Avogadro's law, but also giving him his own number. Maybe the most important number in chemistry. Certainly one of my very favorite numbers, but we'll get to that later. Thank you for watching this episode of Crash Course Chemistry. If you were paying attention, you now know the story of how we went from alchemists who thought that the element of fire hid inside of substances just clamoring to get out, to chemists who understood the law of conservation of mass as proposed by a decapitated aristocrat. Greater understanding of how chemical compounds work thanks to a pharmacist and a school teacher, and eventually a complete understanding of what atoms and molecules are thanks to a neglected Italian house elf nobleman. This episode of Crash Course Chemistry, it was written by myself, filmed and directed by Michael Aranda, and edited by Nick Jenkins. The script was edited by Blake T. Pastino and Dr. Heiko Langner. Michael Aranda is also our sound designer, Caitlin Hoffmeister is our script supervisor, and our graphics team is Thought Cafe. If you have any questions, please ask them in the comments below. Thank you for learning with us here at Crash Course Chemistry. Hello, I'm Hank Green. Welcome to Crash Course Chemistry. Today, we're talking about the most important table ever. Not the table where they signed the Declaration of Independence, nor any table of contents, nor this table right here, nor the stone table of Aslan. Nay, it is the periodic table of elements, a concise, information-dense catalog of all of the different sorts of atoms in the universe. Today I want to talk a bit about the creation of this table, which is, to be clear, one of the crowning achievements of human thought. To start out, though, let's close our eyes and pretend. Imagine you're in Siberia, and you're a 13-year-old boy, and your father, who was a professor but had gone blind, leaving your family of more than 10 brothers and sisters destitute, has just died. I know, downer. Your mom, to support the family, has reopened an abandoned glass-making factory in the small town where you live, largely because she wants to make enough money to send you to school someday. A year passes, the factory burns down. But your mom, she sees your potential. She knows that you have a keen scientific mind and will not see that squandered. So, with your siblings out of the house and on their own, she packs up your belongings, straps them to a horse, and with you in tow, rides 1,200 miles through the Ural Mountains on horseback to a university in Moscow. There, on your behalf, she pleads earnestly and effectively, and they reject you. So together, you ride another 400 miles to St. Petersburg, to the school where your father graduated as a scientist, and as luck, or extreme, insane, undeniably Russian persistence would have it, they accept you, and your saddle-worn butt, as a pupil. Your mother, having completed her mission, promptly dies. If you're doing your imagining as I've told you, you might feel a tremendous debt to your mother and a very deep desire to ensure that you achieve something on par with the sacrifices she made for you. And maybe that's one reason why Dmitri Ivanovich Mendeleev became the crown jewel of Russian science and a theorist who revolutionized how we see the world. Mendeleev spent a great deal of time in laboratories as a student, studying the burgeoning new field of chemistry. He worked with all the elements that you could work with at the time, and his knowledge gave him unique insights into their properties. Those insights would come in handy. Let's all imagine we're Mendeleev again. I like doing that. And that we know a bunch of stuff about chemistry, which, you don't yet, but we're imagining. So it's the 1860s. And about 60 elements are known to mankind, and their atomic weights are mostly known as well. So the simplest thing was just to sort them in order of their atomic weights. But interestingly, you, because you're clever pants, realized that the most significant relationships seem to have nothing to do with the atomic weight. Lithium, sodium, potassium, and rubidium were all extremely prone to reacting with chlorine, fluorine, iodine, and bromine. Beryllium, magnesium, calcium, and strontium were all similar but less reactive. But with a quick inspection, you, and to be fair, a number of other chemists, realized that there was a relationship between atomic weights, but it's periodic. At the beginning of the list of elements, characteristics repeat every 7 elements. On the side here, we now know that it's every 8 elements, but in the 1860s, elements were studied based on their reactivity. So the non-reactive noble gases had not yet been discovered, so the period occurred every 7 elements. As the mass of the elements increases, the repetition starts to look a little less periodic, though it's certainly still there, it just isn't perfect. Some of your colleagues, they're saying, well, such is life. It was perfect repetition early on, but later in the list it gets a little funky. But not you. You become obsessed. Obsessed with the perfection of the periodicity. You write out the names and weights and properties of elements on cards, you lay them across your desk, shuffle them, tear them to pieces in frustration until one day you realize simply missing cards. The numbers aren't working, not because there's something wrong with your ideas, but because some elements simply haven't been discovered yet. Armed with this insight, you insert gaps into the table, and things suddenly fall perfectly into place. 7 element periods for the first 2 rows, with hydrogen in its own category, 18 element periods for the next 2 rows. You're so certain that you predict the properties of these missing elements. And when a French scientist comes along and says that he has in fact discovered one of them, you argue with him, saying that you discovered it first in your mind. And when you see his data and it doesn't match yours, you publish a paper saying his data for the new element he discovered is wrong. That's how certain you are of yourself and this beautiful new theoretical framework you created. And you know what the really crazy thing is? You're right. That French guy's data was wrong. You, never having examined the element he discovered, knew more about it than he did. Because you are Mendeleev, master of the elements. Okay, we're done imagining for the episode. That was fun, though. The different groups Mendeleev had identified are a lot of the same group that we studied today. Starting at the left, we have the soft, shiny, extremely reactive alkaline metals. So reactive, in fact, that they have to be stored in inert gases or oil to prevent them from reacting with the atmosphere. Alkaline metals want nothing more than to dump off an electron and form a positive ion, or cation. And they're always jonesing to hook up with a hottie from the other side of the table. So, of course, seeing as they're so reactive, you don't find hunks of them lying around in nature. Instead, chemists must extract them from compounds containing them. Next, you have the alkaline earth metals. Reactive metals, but not as reactive as the alkali metals, forming cations with 2 positive charges instead of just 1. Calcium, shown here, undergoes a very similar reaction to sodium and water, just a little more slowly, producing a little less heat. The middle body area of the table is made up of a nice solid rectangle of transition metals. These are the metals you think of as metals, with iron and nickel and gold and platinum. The majority of elements are metals. They're fairly unreactive, great conductors of heat, but more importantly for us, good conductors of electricity. They're malleable and can be bent and formed and hammered into sheets, and they're extremely important in chemistry, but overall surprisingly similar to each other. On the far right, just over from the noble gases, the halogens make up a set of extremely reactive gases that form negative ions, or anions with 1 negative charge, and love to react with the alkali and alkaline earth metals. The rectangle between the halogens and the transition metals contain a peculiar scattershot of metals, metalloids, gases, and nonmetals. These guys don't end up as ions unless you take extreme action and start shooting other ions at them, so generally a bit boring over here, though lots of interesting covalent organic chemistry. We'll get to that. Down below, in their own little island, are the lanthanides and actinides, metals that were largely undiscovered in Mendeleev's day because they're so similar that it's next to impossible to separate them from each other. And finally, on the far, far right, also undiscovered when Mendeleev built his chart, the completely unreactive noble gases. Like a lot of other obsessive scientists, Mendeleev never thought he was done with his table, so he held it back for quite a while, only publishing it as part of a new chemistry textbook he was working on as a way to make some quick cash that he needed. And as with many other scientific revelations, there were a number of other people hot on this discovery's trail. As many as 6 people published on the periodicity of elements at roughly the same time as Mendeleev, but a few things set him apart. 1, he was obsessive. He knew the data better than anyone else and had spent a ton of time working on a theory that many people thought was just an interesting little quirk. And 2, he realized in a way no one else did that the idea of periodicity had far-reaching consequences. It seems as if he had a deep belief in the cosmic importance of what he was doing, almost a religious fascination. Mendeleev believed in God, but also he believed that organized religions were false paths to the unknowable nature of God. I like to believe that he thought he saw some divine pattern in his tables, and Mendeleev felt as if he was coming to know God in a way that no other man ever had. To be clear, this is pure conjecture. And as we now know, the periodicity of elements is a physical phenomenon. It's a function of electrons, which are, in some ways, pretty dang peculiar, but certainly not at all mystical. But we'll get to that peculiar physical reality in the next episode. The periodic table that we know and love, I love it anyway, is a representation of reality, a way of understanding and sorting the universe as it exists. But that form of the table is not by any means set in stone. Indeed, a contemporary of Mendeleev envisioned the table set onto a screw or cylinder with the elements wrapping around from one side to another. While Mendeleev's table looks more like a map up on a wall, Deschamps-Courtois, a geologist, envisioned more of a globe. Unfortunately for Deschamps-Courtois, no publisher could figure out how to print his cylindrical 3-dimensional table, and so he published his paper without a graphical representation of his periodic cylinder of the elements, and it was largely ignored. I guess they didn't have papercraft back then. I am a huge fan of this cut and tape model of the periodic table. You can make your own, there's a link in the description. And there are also a ton of other designs for periodic tables that have various advantages over the one that we're all familiar with. Our periodic table as it stands is really a little bit unhappy with itself, frankly. The lanthanides and actinides really should be part of the table, but we separate them out because it's hard to fit that on a piece of paper. Really, this is what it should look like. And really, it would be best if it wrapped around into a circle so that fluorine and neon and sodium were all next to each other instead of being on the opposite sides of the map, because they're just 1 proton away. Mendeleev's contribution, nonetheless, is more powerful than at first it seemed. He ended up forming a guide to help future chemists understand things that wouldn't be discovered for 25, 50, even 100 years. Indeed, after Mendeleev's theories were published and accepted, the overwhelming cry from the scientific community was, why? 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 And though Mendeleev was not himself concerned with this stuff, he actually denied the existence of atoms, or indeed anything he couldn't see with his own eyes, it turned out that the answer to the first why was the electron. That sneaky little electron, Mendeleev, if he'd been around to see their discovery, he would have hated them. But you will have a healthy respect for them after you learn all about them on the next episode of Crash Course Chemistry.
I'm going to speak about a problem that I have, and that's that I'm a philosopher. When I go to a party and people ask me, what do I do, and I say I'm a professor, their eyes glaze over. When I go to an academic cocktail party, and there's all the professors around, they ask me what field I'm in, and I say philosophy, their eyes glaze over. When I go to a philosopher's party, and they ask me what I work on, and I say consciousness, their eyes don't glaze over. Their lips curl into a snarl. And I get hoots of derision and cackles and growls because they think that's impossible. You can't explain consciousness. The very chutzpah of somebody thinking that you could explain consciousness is just out of the question. My late lamented friend Bob Nozick, fine philosopher, in one of his books, Philosophical Explanation, he's commenting on the ethos of philosophy, the way philosophers go about their business. And he says, you know, philosophers love rational argument. And he says, it seems as if the ideal argument for most philosophers is you give your audience the premises, and then you give them the inferences and the conclusion. And if they don't accept the conclusion, they die. Their heads explode. The idea is to have an argument that is so powerful that it knocks out their minds. But in fact, that doesn't change people's minds. It's very hard to change people's minds about something like consciousness. And I finally figured out the reason for that. The reason for that is that everybody's an expert on consciousness. We heard the other day that everybody's got a strong opinion about video games. They all have an idea for a video game, even if they're not experts. But they don't consider themselves experts. They have strong opinions. I'm sure that people here who work on, say, climate change and global warming, or on the future of the internet, they encounter people who have very strong opinions about what's going to happen next. But they probably don't think of these opinions as expertise. They're just strongly held opinions. But with regard to consciousness, people seem to think, each of us seems to think, I am an expert. Simply by being conscious, I know all about this. And so you tell